Good evening. I'm so glad you found your way here tonight. There is a question that has puzzled astronomers for decades. If the universe began as a nearly uniform soup of hydrogen and helium, how did it become so structured? How did smooth become lumpy? How did emptiness give way to galaxies, and galaxies arrange themselves into patterns stretching hundreds of millions of light years across? The answer lies in gravity, time, and something we call dark matter, an invisible scaffolding that guided ordinary matter into the cosmic web we observe today. Filaments of galaxies stretching like threads between vast empty bubbles. Clusters containing thousands of galaxies, each bound together by gravitational forces so immense they bend light itself. Tonight we are mapping this architecture. We will begin here, in our own Milky Way, nestled within the local group, a modest gathering of perhaps 80 galaxies. From there, we will pull back to see the Virgo Supercluster, then further still to the Laniakea Supercluster, a structure so vast that light takes 500 million years to cross it. And finally, we will drift into the great cosmic voids, regions where galaxies are scarce and silence stretches for hundreds of millions of light years. If these quiet explorations help you rest, or simply help you see the universe a little differently, please consider liking and subscribing. It helps others find their way here too. Now settle in, let your breathing slow. We have a long way to travel, and the cosmos is patient. Everything that exists, has existed, or will ever exist belongs to a single vast container with no walls, no edges, and no outside. This is the universe. It is not merely the stars scattered across the night sky or the galaxies spinning in the darkness beyond. It is the totality of space, time, matter, energy, and the physical laws that govern their behavior. There is nothing beyond it, because beyond requires space, and all space is contained within it. The universe began approximately 13.8 billion years ago in an event of unimaginable density and temperature. In the first fraction of a second, all the energy that would ever exist was compressed into a region smaller than an atom. The temperature exceeded 10 billion degrees Kelvin. There were no stars, no planets, no atoms, only a seething plasma of fundamental particles and radiation expanding outward at tremendous speed. This expansion was not an explosion into pre-existing space. Space itself was being created, stretching like the surface of an inflating balloon, carrying matter and energy along with it. Within the first 3 minutes, the universe cooled enough for protons and neutrons to fuse into the nuclei of the lightest elements. Roughly 75% of ordinary matter became hydrogen, about 25% became helium, and trace amounts of lithium and beryllium formed as well. These proportions, measured today in ancient stars and primordial gas clouds, match the predictions of nuclear physics with remarkable precision. The heavier elements, carbon, oxygen, iron, gold, did not yet exist. They would be forged much later in the cores of stars and the violence of stellar explosions. For nearly 380,000 years after its birth, the universe remained opaque. Photons could not travel freely because they scattered constantly off the dense soup of charged particles. Then, as expansion continued and temperatures dropped below about 3,000 Kelvin, electrons combined with nuclei to form neutral atoms. Suddenly, light could travel unimpeded. the universe became transparent, and the first light was released. That ancient glow, stretched by 13.8 billion years of cosmic expansion, still fills the universe today as the cosmic microwave background radiation. It has a temperature of just 2.725 Kelvin, barely above absolute zero, and it is the oldest light we can observe. A snapshot of the universe when it was less than 0.003% of its current age. The observable universe, the portion from which light has had time to reach us, spans approximately 93 billion light-years in diameter. This number seems paradoxical given the universe's age of 13.8 billion years, but the expansion of space itself allows distant regions to be farther away than light could have traveled in a static universe. Beyond this observable sphere, more universe almost certainly exists, perhaps infinitely more, but its light has not yet arrived, and perhaps never will. Within this observable volume, astronomers estimate there are roughly 2 trillion galaxies, each containing anywhere from a few million to several trillion stars. The total number of stars may exceed 200 sextillion, a 2 followed by 23 zeros. Between these galaxies stretches the intergalactic medium, a sparse fog of hydrogen and helium atoms, averaging perhaps 1 atom per cubic meter. This is a vacuum far more perfect than any laboratory on Earth can achieve, yet it contains most of the ordinary matter in the universe. Ordinary matter, however, is not the dominant component of the cosmos. It accounts for only about 5% of the total energy content. Another 27% consists of dark matter, a substance that does not emit, absorb, or reflect light, yet exerts gravitational influence on visible matter. Its presence is inferred from the rotation curves of galaxies, the bending of light around massive clusters, and the patterns in the cosmic microwave background. Without dark matter, galaxies would not hold together. Stars would drift apart like leaves scattered by wind. The remaining 68% of the universe's energy content is something even more mysterious: dark energy. This is not a substance in the traditional sense, but rather a property of space itself, a pressure that causes the expansion of the universe to accelerate. Discovered in 1998 through observations of distant supernova, dark energy ensures that galaxies are receding from one another faster and faster with each passing eon. In the far future, this acceleration will carry most galaxies beyond the observable horizon, leaving our descendants in an increasingly isolated cosmic neighborhood. The universe operates according to physical laws that appear constant across all of space and time. The speed of light in a vacuum is always 299,792 kilometers per second, whether measured in a laboratory on Earth or inferred from the spectra of galaxies billions of light-years away. Gravity follows the same equations here as it does in the most distant galaxy clusters. The charge of an electron, the mass of a proton, the strength of nuclear forces. These fundamental constants seem identical everywhere we look. This uniformity allows us to study the cosmos at all, to apply local physics to remote phenomena, to reconstruct the history of the universe from the faint signals reaching our telescopes. Space and time are not separate entities, but woven together into a four-dimensional fabric called space-time. Mass and energy curve this fabric, and the curvature dictates how objects move. A planet orbits a star not because an invisible force pulls it inward, but because the star's mass warps space-time, and the planet follows the straightest possible path through that curved geometry. Near a black hole, space-time curves so severely that not even light can escape. At the largest scales, the overall geometry of the universe appears remarkably flat, meaning parallel lines remain parallel even across billions of light years. Everything in the universe is connected by this shared fabric, by the same physical laws, by a common origin in that initial moment of expansion. The iron in your blood was forged in a star that exploded before the sun was born. The hydrogen in water is primordial, unchanged since those first 3 minutes. The light from distant galaxies carries information about conditions billions of years ago, allowing us to witness the universe's evolution directly. This is the stage upon which all cosmic structures exist. From the smallest grain of dust to the largest web of galaxy clusters, everything occupies a place within this expanding, evolving totality. The universe is not static. It grows, cools, and changes. Stars are born and die. Galaxies collide and merge. The cosmic web stretches and thins. Understanding the universe means understanding this constant transformation, this interplay of gravity and expansion, matter and energy, time and space. And within this immense arena, structure emerges at every scale. The universe is not a uniform fog of particles, but an intricate hierarchy of organization. Matter clumps under gravity's patient pull, forming objects of increasing size and complexity. The smallest of these gravitationally bound structures, the building blocks from which larger systems are assembled, are the worlds we call planets, spheres of rock, gas, and ice, each with its own story written in craters, atmospheres, and magnetic fields. Planets are the first rung on the cosmic ladder of structure, the smallest objects massive enough to have pulled themselves into spheres under their own gravity. They are worlds in the truest sense, distinct places with surfaces or cloud tops, with weather and seasons, with histories stretching back billions of years to the violent birth of their parent stars. To qualify as a planet, an object must meet 3 criteria established by astronomers. It must orbit a star, it must possess enough mass for gravity to crush it into a roughly spherical shape, and it must have cleared its orbital neighborhood of other debris. This last requirement distinguishes planets from the countless smaller bodies that drift through planetary systems, the asteroids, comets, and dwarf planets that never accumulated enough gravitational authority to dominate their surroundings. The mass required for spherical shape is surprisingly modest by cosmic standards. An icy body achieves this roundness at roughly 400 kilometers in diameter, while a rocky object needs perhaps 600 kilometers. Below these thresholds, the structural strength of rock and ice resists gravity's squeeze, allowing irregular potato-like shapes to persist. Above them, gravity wins, and the object relaxes into a sphere over geological timescales, its own weight slowly deforming any mountains or bulges that rise too high. Planets divide into 2 fundamental categories based on their composition: the terrestrial worlds built primarily of rock and metal, and the giant planets constructed mainly of hydrogen, helium, and volatile ices. This division reflects not merely different ingredients, but entirely different formation histories, different internal structures, and different fates. Terrestrial planets form in the inner regions of young planetary systems, where temperatures are too high for volatile compounds to condense into solid form. Within a few astronomical units of a newborn star, 1 astronomical unit being the distance from Earth to the Sun, about 150 million kilometers, only rock and metal can exist as solid grains. These refractory materials, rich in silicon, oxygen, magnesium, and iron, accumulate through countless collisions, building larger and larger bodies over millions of years. The process begins with dust grains smaller than sand, sticking together through electrostatic forces and gentle collisions. These aggregates grow into pebbles, then boulders, then kilometer-sized planetesimals. At this stage, gravity becomes significant, and the largest planetesimals begin sweeping up their neighbors in a process called runaway accretion. Within perhaps 100,000 years, a few dozen planetary embryos emerge, each containing a significant fraction of the solid material in its orbital zone. The final assembly takes longer. Tens of millions of years of giant impacts between these embryos, collisions so energetic they melt entire worlds and strip away atmospheres. Earth itself bears the scars of this violent youth. Our moon likely formed from debris ejected when a Mars-sized body struck the young Earth approximately 4.5 billion years ago, an impact that liquefied both objects and left our planet spinning so fast that a day lasted only 6 hours. The terrestrial planets of our solar system illustrate the diversity possible within this category. Mercury, the innermost, is a dense iron ball just 4,800 kilometers in diameter. Its surface baked to 430 degrees Celsius on the sunlit side, while plunging to minus 180 degrees in permanent shadow. Its enormous iron core, comprising 85% of its radius, suggests that much of its rocky mantle was blasted away by ancient impacts or vaporized by the young sun's intense radiation. Venus, nearly Earth's twin in size at 12,100 kilometers diameter, demonstrates how similar starting conditions can produce radically different outcomes. Its thick carbon dioxide atmosphere, 90 times denser than Earth's, traps solar heat so efficiently that surface temperatures reach 465 degrees Celsius, hot enough to melt lead. Sulfuric acid clouds shroud the planet in perpetual overcast, and the atmospheric pressure at the surface equals that found a kilometer deep in Earth's oceans. Earth, the third terrestrial world, maintains liquid water on its surface, a condition so rare and so crucial for life as we know it, that astronomers define a habitable zone around every star based on where liquid water could persist. Our planet's moderate greenhouse effect, maintained by trace amounts of carbon dioxide and water vapor, keeps global average temperatures around 15 degrees Celsius, some 33 degrees warmer than a bare rock at our distance from the Sun would be. Mars, the outermost terrestrial planet, tells a story of lost potential. At 6,700 kilometers diameter, it is only half Earth's size, and its lower gravity could not retain a thick atmosphere against the solar wind's relentless erosion. Today, its surface pressure is less than 1% of Earth's, and temperatures average minus 60 degrees Celsius. Yet dried river channels, lake beds, and mineral deposits formed by water reveal that Mars once possessed a denser atmosphere and flowing surface water, perhaps 3.5 billion years ago. Beyond the frost line, the distance from a star where water ice can condense, roughly 2.5 to 3 astronomical units in our solar system, planet formation follows a different path. Here, ice is abundant, and solid material is far more plentiful than in the inner system. Planetary cores can grow much larger, reaching 10 to 15 Earth masses before the surrounding gas disk dissipates. At this critical threshold, the core's gravity becomes strong enough to capture hydrogen and helium directly from the disk, triggering runaway gas accretion that can multiply the planet's mass 100-fold in just a few 100,000 years. Jupiter exemplifies this process taken to its extreme. With a mass of 1.9 times 10 to the 27th kilograms, 318 times Earth's mass, and 2.5 times the mass of all other planets combined, Jupiter contains enough material to have become a star had it been roughly 80 times more massive. Its diameter of 140,000 kilometers could swallow 11 Earths laid side by side, yet its average density is only 1.3 grams per cubic centimeter, barely denser than water. Deep within Jupiter, pressures exceed millions of atmospheres, and hydrogen behaves in ways unknown on Earth. Below about 20,000 kilometers depth, the pressure forces hydrogen molecules apart, and the atom's electrons become free to move, creating a metallic form of hydrogen that conducts electricity like a metal. This metallic hydrogen layer, perhaps 40,000 kilometers thick, generates Jupiter's immense magnetic field, 20,000 times stronger than Earth's and extending millions of kilometers into space. Saturn, the second gas giant, is less massive at 95 Earth masses, but even less dense, only 0.7 grams per cubic centimeter, light enough to float on water if a sufficiently large ocean existed. Its famous rings, extending from 7,000 to 80,000 kilometers above the cloud tops, contain billions of particles of nearly pure water ice, ranging from dust grains to house-sized boulders. The rings are surprisingly young, perhaps only 100 million years old, possibly formed when a moon wandered too close and was torn apart by tidal forces. Uranus and Neptune represent a third category, ice giants. Though still massive at 14 and 17 Earth masses respectively, they contain far less hydrogen and helium than Jupiter and Saturn. Instead, their bulk consists of heavier elements, water, ammonia, and methane, compressed into hot, dense fluid layers beneath relatively thin hydrogen-helium atmospheres. Neptune's vivid blue color comes from methane in its upper atmosphere, which absorbs red light and reflects blue. These ice giants orbit at vast distances, Uranus at 19 astronomical units, Neptune at 30, where the original disk contained so little material that they took far longer to form. Some models suggest they actually formed closer to the Sun and migrated outward, scattering smaller bodies as they went, and sculpting the architecture of the outer solar system. The internal heat of giant planets reveals their formation history. Jupiter radiates nearly twice as much energy as it receives from the Sun, powered by slow gravitational contraction that continues to this day, shrinking the planet by roughly 2 centimeters per year. This process, called Kelvin-Helmholtz contraction, converts gravitational potential energy into heat. warming Jupiter's interior to perhaps 20,000 Kelvin at its core. Neptune shows an even greater heat excess, radiating 2.6 times its solar input, though the mechanism remains debated. Every planet, regardless of type, carries information about its birth encoded in its composition, its orbit, and its rotation. The tilt of Uranus, lying nearly on its side with an axial tilt of 98 degrees, speaks of a catastrophic collision early in its history. The retrograde rotation of Venus, spinning backward compared to its orbit, may result from tidal interactions with its thick atmosphere or another ancient impact. The orbital resonances of Jupiter's moons, with Io, Europa, and Ganymede locked in a precise 4:2:1 ratio, reveal billions of years of gravitational fine-tuning. Planets are not merely spheres of matter, but dynamic systems, constantly evolving under the influence of internal heat, stellar radiation, and gravitational interactions. They possess atmospheres that cycle chemicals between surface and sky, magnetic fields that shield or expose them to stellar winds, and geological processes that resurface them over millions of years. Each is a laboratory for physics and chemistry, a world unto itself. Yet planets do not exist in isolation. Most are accompanied by smaller bodies trapped in their gravitational embrace. Moons that range from irregular captured asteroids to worlds as complex as the planets themselves, some harboring subsurface oceans, some with atmospheres, some with geological activity driven by tidal heating rather than internal radioactivity. These smaller companions, the moons, represent one of nature's most elegant expressions of gravitational hierarchy. A moon is any natural satellite orbiting a planet, dwarf planet, or even an asteroid. A body caught in the gravitational well of a larger neighbor, forever falling toward it, yet forever missing, tracing ellipses through the vacuum of space. The solar system alone contains over 200 known moons, ranging from irregular chunks of rock barely a kilometer across to worlds larger than the planet Mercury. The formation of moons follows several distinct pathways, each leaving characteristic signatures in their orbits and compositions. Some moons coalesced from the same rotating disk of gas and dust that formed their parent planet, condensing in place like miniature planetary systems within planetary systems. The four largest moons of Jupiter, Io, Europa, Ganymede, and Callisto, collectively known as the Galilean moons, formed this way approximately 4.5 billion years ago. They orbit in nearly circular paths aligned with Jupiter's equator, their compositions varying systematically with distance from the giant planet. Io, closest to Jupiter at 421,700 kilometers, is dense and rocky, stripped of volatiles by the young Jupiter's intense heat. Ganymede, orbiting at 1.07 million kilometers, contains roughly equal parts rock and water ice, massive enough at 2,634 kilometers in radius to qualify as the largest moon in the solar system. Larger, in fact, than Mercury, though only about half as massive due to its lower density of 1.94 grams per cubic centimeter. Other moons arrived as captives, wandering bodies from elsewhere in the solar system that strayed too close to a planet and became trapped in its gravitational embrace. These captured moons betray their origins through irregular orbits, highly elliptical, steeply inclined, or even retrograde, circling opposite to their planet's rotation. Triton, Neptune's largest moon at 2,707 kilometers in diameter, orbits backward relative to Neptune's spin, a clear signature of capture. Its surface temperature of -235 degrees Celsius makes it one of the coldest objects in the solar system. Yet geysers of nitrogen gas erupt from beneath its frozen surface, driven by feeble solar heating that sublimates subsurface ices. Triton almost certainly originated in the Kuiper Belt, the ring of icy bodies beyond Neptune, before a close encounter redirected it into Neptune's gravitational prison. The capture process would have been violent, requiring Triton to lose orbital energy through interactions with other moons or a primordial disk of debris. Moons that no longer exist, consumed or ejected during Triton's arrival. The most dramatic formation mechanism belongs to Earth's own companion. The Moon, 3,474 kilometers in diameter and orbiting at an average distance of 384,400 kilometers, was born from catastrophe. Approximately 4.5 billion years ago, a Mars-sized body called Theia struck the young Earth at an oblique angle, vaporizing both the impactor and a significant portion of Earth's mantle. The resulting cloud of superheated debris, reaching temperatures exceeding 10,000 Kelvin, spread into a disk around the wounded Earth and coalesced within perhaps a century into the Moon. This giant impact hypothesis explains the Moon's peculiar properties: its low iron content compared to Earth, its identical oxygen isotope ratios suggesting shared material, and its initial proximity. The young Moon orbited at perhaps 25,000 kilometers, close enough to raise rock tides on Earth's molten surface. Tidal interactions have since pushed the Moon outward at a rate of 3.8 centimeters per year, a recession that continues today, measurable by laser reflectors left by Apollo astronauts. Tidal forces, in fact, dominate the physics of moons. These differential gravitational pulls, stronger on the near side of a body than the far side, stretch moons along the line, connecting them to their parent planet. For moons in elliptical orbits, this stretching varies as the Moon moves closer and farther from its planet, flexing the Moon's interior and generating heat through friction. Io experiences this tidal heating to an extreme degree. Locked in orbital resonance with Europa and Ganymede, for every orbit Ganymede completes, Europa completes 2, and Io completes 4, Io's orbit is forced into a slight ellipse that prevents tidal equilibrium. The resulting internal friction generates approximately 100 trillion watts of heat, making Io the most volcanically active body in the solar system. Over 400 active volcanoes dot its sulfur-stained surface, erupting plumes that reach 500 kilometers into space, painting the Moon in shades of yellow, red, orange, and black. Io's entire surface is replaced by volcanic deposits roughly every million years, erasing impact craters almost as quickly as they form. Europa, the next moon outward, experiences gentler but still significant tidal heating. Its icy surface, crisscrossed by reddish-brown fractures and remarkably free of large craters, conceals a global ocean of liquid water, perhaps 100 kilometers deep, more water than all of Earth's oceans combined. The ice shell above, estimated at 15 to 25 kilometers thick, flexes and cracks as Europa orbits Jupiter, allowing warmer ice or even liquid water to well up and resurface the Moon. The reddish material staining the fractures may be salts or organic compounds from the ocean below, delivered to the surface by geological processes, with liquid water, chemical energy from rock-water interactions, and the organic building blocks common throughout the solar system. Europa represents one of the most promising environments for extraterrestrial life. Saturn's moon Enceladus, only 504 kilometers in diameter, demonstrates that even small moons can harbor oceans. Despite its diminutive size, Enceladus possesses a subsurface sea beneath its south polar region, detected through the dramatic geysers that erupt from fractures nicknamed tiger stripes. These plumes spray water ice, sodium salts, silica particles, and simple organic molecules into space at velocities exceeding 400 meters per second, feeding Saturn's diffuse E-ring. The silica particles indicate hydrothermal activity on Enceladus's ocean floor, hot water interacting with rock at temperatures above 90 degrees Celsius, conditions reminiscent of Earth's deep-sea vents where life thrives independent of sunlight. Titan, Saturn's largest moon, presents an entirely different kind of world. At 5,150 kilometers in diameter, Titan exceeds Mercury in size and possesses the only dense atmosphere of any moon in the solar system, a nitrogen-rich envelope with a surface pressure of 1.5 atmospheres, 50% higher than Earth's sea level. The temperature at Titan's surface hovers around -179 degrees Celsius, cold enough for methane and ethane to exist as liquids. Radar mapping by the Cassini spacecraft revealed lakes and seas of liquid hydrocarbons concentrated near Titan's poles, with Kraken Mare spanning approximately 400,000 square kilometers, larger than Earth's Caspian Sea. Rain falls on Titan, not water but methane, carving river channels into the water ice bedrock and filling basins with hydrocarbon seas. Beneath this alien hydrological cycle, a water-ammonia ocean likely exists, sandwiched between layers of high-pressure ice, adding Titan to the growing list of ocean worlds. The diversity of moons extends to their surfaces and compositions. Mimas, another of Saturn's moons, bears a crater so large relative to its 396-kilometer diameter that the impact nearly shattered it. Herschel crater spans 130 kilometers, giving Mimas an uncanny resemblance to the Death Star from popular fiction. Miranda, orbiting Uranus, displays a surface so chaotically jumbled that early observers speculated it had been shattered and reassembled. Its Verona Rupi's cliff drops 20 kilometers, the tallest known cliff in the solar system. Hyperion, also at Saturn, tumbles chaotically through space, its rotation unpredictable from one orbit to the next due to its irregular shape and gravitational interactions with Titan. Even asteroids possess moons. Ida, a 56-kilometer-long asteroid in the main belt, hosts a tiny companion named Dactyl, only 1.4 kilometers across, discovered in 1993 by the Galileo spacecraft. Since then, over 400 asteroid moons have been identified, revealing that gravitational binding occurs at scales far smaller than planets. Some asteroids are binary systems with nearly equal-sized components. Others host multiple satellites, and a few are contact binaries. two bodies resting against each other, held together by gravity so weak that a human could escape by jumping. Moons stabilize their parent planets in subtle ways. Earth's moon stabilizes our planet's axial tilt at approximately 23.4 degrees, preventing the wild oscillations that would otherwise occur over millions of years due to gravitational tugs from Jupiter and other planets. Mars, lacking a large moon, has experienced axial tilts ranging from nearly 0 to over 60 degrees throughout its history, driving extreme climate variations. The moon also slows Earth's rotation through tidal friction. Days were only 6 hours long shortly after the moon's formation and have lengthened steadily since. These gravitationally bound companions, from captured asteroids to ocean-bearing worlds, demonstrate that complexity emerges at every scale where gravity can gather matter. Yet moons are themselves components of larger systems, the planetary systems where multiple worlds orbit a central star, each following paths dictated by the same gravitational laws, their orbits interlocking in patterns that can remain stable for billions of years, or collapse into chaos within mere millions. The architecture of these orbital systems reveals itself not as random scattering, but as precise mechanical arrangement, each world tracing its path according to laws that Johannes Kepler first glimpsed 4 centuries ago, and that Isaac Newton explained through the mathematics of universal gravitation. A planetary system is the complete ensemble of objects gravitationally bound to a single star or stellar group. Planets, moons, asteroids, comets, dust, and gas, all moving in coordinated patterns around their central luminary. Our own solar system spans roughly 100,000 astronomical units from the Sun to the outer edge of the Oort cloud, where 1 astronomical unit equals the 150 million kilometers separating Earth from the Sun. At the speed of light, a signal would take over 18 months to cross this entire domain. The formation of such systems begins in the same nebular cradles that birth stars themselves. As a molecular cloud core collapses under gravity, conservation of angular momentum forces the infalling material to flatten into a rotating disk, the protoplanetary disk. This disk of gas and dust, typically spanning 100 to 1,000 astronomical units and containing roughly 1% of the central protostar's mass, becomes the raw material from which all planetary bodies will eventually coalesce. Temperatures in these disks vary dramatically with distance from the young star. Within a few astronomical units, temperatures exceed 1,000 Kelvin, hot enough to vaporize most compounds, while beyond the frost line, located at roughly 2.7 astronomical units in our solar system, temperatures drop below 170 Kelvin, allowing water ice to condense as solid grains. This temperature gradient creates a fundamental division in planetary architecture. Inside the frost line, only refractory materials survive: silicates, iron, nickel, and aluminum oxides, limiting the mass available for planet building. The terrestrial planets of our inner solar system reflect this constraint. Mercury, Venus, Earth, and Mars together contain less than 2 Earth masses of material. Beyond the frost line, ice adds to the inventory of solid building blocks, increasing the available mass by a factor of 4 or more. This abundance allows planetary cores to grow large enough, roughly 10 Earth masses, to gravitationally capture the hydrogen and helium gas that dominates the disk, spawning gas giants like Jupiter at 318 Earth masses and Saturn at 95 Earth masses. The process unfolds through hierarchical accretion spanning millions of years. Dust grains collide and stick, forming centimeter-sized pebbles. Pebbles accumulate into kilometer-scale planetesimals through processes still debated. Perhaps gravitational instability in dense dust layers, perhaps streaming instabilities that concentrate particles against the gas flow. Planetesimals then collide and merge, the largest ones growing fastest because their stronger gravity sweeps up material from wider feeding zones. Within 1 to 3 million years, planetary embryos of lunar to Mars mass dominate the inner disk, while in the outer regions, cores of 5 to 15 Earth masses begin their rapid gas accretion phase. Our solar system preserves evidence of this violent assembly. The Moon likely formed from debris ejected when a Mars-sized body named Theia struck the proto-Earth roughly 4.5 billion years ago, the impact so energetic that both bodies partially vaporized. Mercury's enormous iron core, comprising 70% of its mass compared to Earth's 32%, suggests a catastrophic collision stripped away much of its rocky mantle. Uranus rotates on its side, its axis tilted 98 degrees from its orbital plane, almost certainly the result of one or more giant impacts during the final stages of planet formation. The spacing of planetary orbits follows patterns that hint at underlying physical principles. In 1766, Johann Titius noticed that the distances of known planets from the Sun roughly followed a geometric progression, a relationship later promoted by Johann Bode. While the Titius-Bode law fails for Neptune and lacks rigorous theoretical foundation, it reflects a real phenomenon. Planets cannot form too close together without gravitationally perturbing each other into crossing orbits and eventual collision or ejection. The Hill sphere of a planet, the region where its gravity dominates over the Sun's, sets a minimum spacing. For Earth, this sphere extends roughly 1.5 million kilometers, about 4 times the lunar distance. Stable planetary systems typically maintain separations of at least 10 to 20 mutual Hill radii between adjacent planets. Orbital resonances add another layer of structure to planetary systems. When the orbital periods of two bodies form a simple integer ratio, gravitational interactions repeat in regular patterns that can either stabilize or destabilize their orbits. Jupiter and Saturn approach a 5-to-2 resonance, their orbital periods of 11.86 and 29.46 years, producing repeated alignments that may have driven the late heavy bombardment roughly 3.9 billion years ago, when gravitational reshuffling sent asteroids and comets careening through the inner solar system. Pluto survives despite crossing Neptune's orbit because it occupies a 3-to-2 resonance with the ice giant, completing 2 orbits for every 3 of Neptune's, ensuring the two bodies never approach closely. The discovery of exoplanetary systems has revealed architectures radically different from our own. Hot Jupiters, gas giants orbiting their stars in mere days at distances of 0.05 astronomical units or less, challenged the assumption that giant planets must form beyond the frost line. These worlds likely migrated inward through gravitational interactions with the protoplanetary disk, or through scattering events with other planets. The TRAPPIST-1 system packs 7 Earth-sized planets within 0.06 astronomical units of their red dwarf star, all locked in a chain of resonances. The orbital periods form ratios of 8 to 5, 5 to 3, 3 to 2, 3 to 2, 4 to 3, and 3 to 2 moving outward. Such tight, resonant chains suggest smooth migration through a gas-rich disk, rather than the violent collisions that shaped our inner solar system. Kepler-11, a sun-like star 2,000 light-years distant, hosts 6 planets with masses between 2 and 13 Earth masses, all orbiting within a region smaller than Venus's orbit around our Sun. The system's compactness and the planet's low densities, suggesting thick hydrogen-helium envelopes, indicate formation in a gas-rich environment, followed by minimal subsequent disruption. In contrast, the HR 8799 system displays 4 gas giants of 5 to 10 Jupiter masses orbiting between 15 and 70 astronomical units, directly imaged against the glare of their young bright host star. These massive worlds at large distances challenge core accretion models and may have formed through direct gravitational collapse of disk material. The long-term stability of planetary systems depends on subtle gravitational interactions accumulating over billions of years. Our own solar system, despite appearing orderly, exists in a state of marginal stability. Numerical simulations extending billions of years into the future reveal a small but non-zero probability that Mercury's orbit could become chaotic, potentially leading to collision with Venus or the Sun, or ejection from the solar system entirely. The 8 planets exchange angular momentum through secular resonances, slow oscillations in orbital parameters driven by the averaged gravitational influence of all other planets. Jupiter, containing more mass than all other planets combined, dominates these interactions, its gravity shepherding the asteroid belt and preventing the formation of a planet between Mars and itself. Debris disks surrounding mature stars reveal the ongoing processes of planetary system evolution. Fomalhaut, a bright star 25 light-years away, hosts a narrow ring of dust and ice between 133 and 158 astronomical units from the star, its sharp inner edge suggesting gravitational sculpting by an unseen planet. Epsilon Eridani, just 10.5 light-years distant, displays multiple dust belts analogous to our asteroid and Kuiper belts, along with at least one confirmed Jupiter mass planet. These debris structures represent the remnants of planet formation, continuously replenished by collisions among asteroids and comets that grind larger bodies into dust. The outer reaches of planetary systems fade gradually into interstellar space. Our Sun's gravitational influence extends roughly 2 light-years before the tidal forces of the galaxy, and passing stars begin to dominate. The Oort cloud, a hypothetical shell of trillions of icy bodies at distances of 2,000 to 100,000 astronomical units, marks this transition zone. Comets occasionally fall inward from this reservoir, their orbits perturbed by passing stars or the galactic tide, the differential gravitational pull of the Milky Way's mass distribution. These visitors from the edge of the solar system carry pristine material from the earliest epoch of planet formation, their ices and organics unchanged for 4.6 billion years. Every planetary system represents a unique outcome of the same physical processes: gravitational collapse, angular momentum conservation, accretion, migration, and dynamical evolution. The diversity revealed by exoplanet surveys suggests that our solar system, with its clear division between inner rocky worlds and outer gas giants, may be unusual rather than typical. Yet all these systems share a common foundation. They orbit stars, the nuclear furnaces whose light and gravity define the boundaries of each planetary domain. These stars themselves vary enormously in mass, temperature, luminosity, and lifetime, their properties determining what kinds of planetary systems can form and how long those systems might persist. Stars are the fundamental engines of the cosmos, the sources of nearly all light that illuminates the universe, and the forges where almost every element, heavier than hydrogen and helium, comes into existence. Without stars, the universe would remain a cold, dark expanse of primordial gas, devoid of the chemical complexity necessary for planets, moons, and life itself. Each star is a sphere of plasma held together by its own gravity, its core a nuclear furnace where temperatures exceed 10 million Kelvin and pressures crush hydrogen nuclei together with such force that they fuse into helium, releasing energy according to Einstein's famous equation relating mass and energy. The process begins in the hearts of molecular clouds, those vast reservoirs of cold, gas, and dust that drift through galaxies. When a region of such a cloud becomes dense enough, perhaps triggered by a nearby supernova's shockwave or the gravitational perturbation of a passing spiral arm, it begins to collapse under its own weight. As the material falls inward, it heats up, converting gravitational potential energy into thermal energy. A protostar forms at the center, growing as it accretes surrounding material. For a cloud fragment containing one solar mass of material, this collapse phase lasts roughly 100,000 years, a mere heartbeat in cosmic terms. The critical threshold arrives when the core temperature reaches approximately 10 million Kelvin. At this temperature, hydrogen nuclei, protons, move fast enough to overcome their mutual electrical repulsion and approach close enough for the strong nuclear force to bind them together. This is nuclear fusion, the process that powers every star in the universe. In stars like the Sun, the dominant reaction is the proton-proton chain, where 4 hydrogen nuclei ultimately combine to form one helium nucleus. The helium nucleus has slightly less mass than the 4 original protons, about 0.7% less, and this missing mass converts directly into energy. The Sun fuses approximately 620 million metric tons of hydrogen into helium every second, releasing energy equivalent to 384.6 septillion watts, a luminosity that has remained remarkably stable for 4.6 billion years. The mass of a star determines nearly everything about its existence: its temperature, its color, its luminosity, its lifespan, and its ultimate fate. Astronomers classify stars using the Morgan-Keenan system, assigning spectral types based on surface temperature. The sequence runs O, B, A, F, G, K, M, from hottest to coolest, with additional categories for brown dwarfs and other exotic objects. O-type stars blaze with surface temperatures exceeding 30,000 Kelvin, their light dominated by ultraviolet radiation, their masses ranging from 15 to over 100 times that of the Sun. These stellar giants burned through their nuclear fuel with profligate speed, living only a few million years before exhausting their hydrogen and exploding as supernovae. At the opposite extreme, M-type red dwarfs possess surface temperatures between 2,400 and 3,700 Kelvin, their dim red glow barely visible to human eyes. These stars contain between 0.08 and 0.45 solar masses, and their measly energy consumption grants them lifespans measured in trillions of years, far longer than the current age of the universe. Proxima Centauri, the nearest star to our solar system at 4.24 light-years distant, is such a red dwarf with a mass of 0.12 solar masses and a luminosity only 0.0017 times that of the Sun. Despite its proximity, it remains invisible to the naked eye, requiring a telescope to detect. The Sun itself occupies a middle position as a G-type yellow dwarf, with a surface temperature of 5,778 Kelvin and a mass that defines the solar mass unit used throughout astronomy. Its diameter spans 1.39 million kilometers, large enough to contain 1.3 million Earths. Light leaving the Sun's surface takes 8 minutes and 20 seconds to reach Earth, traveling at 299,792 kilometers per second across the 150 million kilometer gulf. This distance defines the astronomical unit, the baseline measure for distances within planetary systems. The relationship between stellar mass and luminosity follows a steep power law. A star twice as massive as the Sun shines not twice as bright, but roughly 11 times brighter. A star 10 times the Sun's mass blazes with a luminosity 3,000 times greater. This relationship explains why massive stars exhaust their fuel so quickly despite having more of it. They burn through their reserves at rates that far outpace their greater supply. A star of 25 solar masses might contain enough hydrogen to fuel the Sun for 250 billion years. Yet it consumes this fuel in only 7 million years, shining with a luminosity 80,000 times solar. Inside every star, a delicate balance maintains stability. Gravity pulls inward, attempting to collapse the star into a point. Radiation pressure and thermal pressure push outward, generated by the energy released in nuclear fusion. This hydrostatic equilibrium persists as long as fusion continues, the star adjusting its structure to maintain balance. If fusion rates increase, the core expands and cools slightly, reducing the reaction rate. If fusion decreases, the core contracts and heats, accelerating the reactions. This self-regulating feedback keeps main sequence stars remarkably stable over billions of years. The internal structure of a star depends critically on its mass. In stars below about 0.35 solar masses, convection dominates throughout the entire interior, with hot plasma rising from the core to the surface and cooler material sinking back down, mixing the star's contents like a pot of boiling water. In stars between 0.35 and 1.3 solar masses, including the Sun, a radiative zone surrounds the core, where energy travels outward as photons bouncing between atoms, while a convective zone occupies the outer layers. In more massive stars, this arrangement reverses. Convection dominates the core, while radiation transports energy through the outer regions. The journey of energy from a star's core to its surface is remarkably slow. A photon generated in the Sun's core does not travel directly outward, but instead bounces randomly between atoms, absorbed and re-emitted countless times. This random walk takes an average of 170,000 years before the energy finally reaches the surface and escapes into space. The photon that warms your face on a summer afternoon began its journey when Neanderthals still walked the Earth, when ice sheets covered much of Europe, when the constellations held different shapes due to stellar proper motion. Stars do not exist in isolation, but form in clusters and associations, born from the same molecular cloud and sharing similar compositions. The chemical makeup of a star reflects the material from which it formed, which in turn reflects the history of nucleosynthesis in previous stellar generations. Astronomers measure stellar metallicity, the abundance of elements heavier than helium, as an indicator of when and where a star formed. The oldest stars in the galaxy, formed within the first billion years after the Big Bang, contain metallicities less than 1% of the Sun's, their birth clouds composed almost entirely of primordial hydrogen and helium. Younger stars like the Sun incorporate the processed material ejected by previous stellar generations, their higher metallicities enabling the formation of rocky planets rich in silicon, iron, and oxygen. The distribution of stellar masses at birth follows a pattern called the initial mass function, discovered by astronomer Edwin Salpeter in 1955. This function reveals that low-mass stars vastly outnumber high-mass stars. For every star born with 10 solar masses, roughly 2,000 stars form with 1 solar mass, and roughly 20,000 form with 0.1 solar masses. Red dwarfs constitute approximately 75% of all stars in the Milky Way, their dim glow contributing only a small fraction of the galaxy's total luminosity, despite their overwhelming numbers. The nearest stars to Earth beyond the Sun form a sparse neighborhood. After Proxima Centauri and its companions, Alpha Centauri A and B at 4.37 light-years, Barnard's star lies 5.96 light-years distant, a red dwarf moving across the sky faster than any other star, 10.3 arc-seconds per year, a motion that would carry it the width of the full moon in just 180 years. Wolf 359 at 7.86 light-years, Lalande 21185 at 8.31 light-years, and Sirius at 8.60 light-years complete the roster of stars within roughly 9 light-years. Sirius, the brightest star in Earth's night sky, achieves this distinction through a combination of intrinsic luminosity, 25 times that of the Sun, and relative proximity. Yet even the nearest stars remain impossibly remote by human standards. If the Sun were reduced to the size of a grain of sand 1 millimeter across, Earth would orbit at a distance of 10 centimeters, and Proxima Centauri would lie 29 kilometers away. The fastest spacecraft ever launched, the Parker Solar Probe, reaches speeds of 192 kilometers per second during its closest solar approaches. Yet even at this velocity, a journey to Proxima Centauri would require over 6,600 years. Stars mark time for the universe, their steady fusion reactions providing the energy that drives planetary climates, powers photosynthesis, and enables the chemistry of life. Their deaths seed space with the heavy elements necessary for new generations of stars and planets. Some stars end quietly, shedding their outer layers as planetary nebulae while their cores contract into white dwarfs. Others explode violently as supernovae, briefly outshining entire galaxies and forging elements heavier than iron in the fury of their collapse. Still others leave behind neutron stars or black holes, objects so dense that they warp space-time itself. These stellar remnants represent the endpoints of stellar evolution, the final states that await every star after its nuclear fuel exhausts. Yet stars rarely exist in isolation. The same gravitational forces that shape their birth from collapsing clouds of gas also bind them to one another, creating systems where 2, 3, or even 7 stars orbit a common center of mass. These binary and multiple star systems are not cosmic oddities, but the norm. Surveys of stellar populations revealed that roughly half of all Sun-like stars have at least one gravitational companion. And among the most massive stars, the fraction rises to nearly 90%. The solitary existence of our own Sun, drifting alone through the Orion Spur with only planets for company, represents the minority condition in a universe where stars prefer partnership. The physics of binary formation begins in the same molecular clouds that birth individual stars. As a dense core collapses under its own gravity, conservation of angular momentum causes it to spin faster, much as a figure skater spins more rapidly when pulling in their arms. This rotation flattens the collapsing material into a disk, but if the angular momentum is too great, the cloud may fragment into 2 or more distinct clumps, each collapsing independently to form a separate star. Alternatively, gravitational instabilities in the disk itself can spawn companion stars, or close encounters in dense stellar nurseries can capture passing stars into bound orbits. The result is a population of stellar pairs and multiples with orbital periods ranging from mere hours to millions of years. The closest binary systems, called contact binaries, orbit so tightly that the stars actually touch, their surfaces merging into a single peanut-shaped envelope of shared gas. These systems complete orbits in less than a day, their components whirling around each other at speeds exceeding 200 kilometers per second. The star W Ursae Majoris, located roughly 170 light-years from Earth, exemplifies this configuration. Its 2 components, each slightly less massive than the Sun, orbit their common center every 8 hours, their surfaces heated to approximately 5,800 Kelvin by the friction of their interaction. Material flows continuously between the stars, and their ultimate fate may be merger into a single, more massive star, or a violent explosion if conditions align. Slightly wider binaries maintain distinct surfaces, but still interact through gravity's invisible threads. In these semi-detached systems, one star has expanded beyond its Roche lobe, the teardrop-shaped region within which material remains gravitationally bound to that star rather than its companion. Gas streams from the bloated star onto its partner, often forming an accretion disk that glows with the heat of infalling matter. The system Algol, the demon star, located 90 light-years away in the constellation Perseus, demonstrates this process. Every 2.87 days, the dimmer, larger star passes in front of its brighter companion, causing Algol's apparent brightness to drop by more than a full magnitude. Ancient astronomers noticed this periodic dimming and associated it with malevolent influences, unaware that they were witnessing the geometric dance of two stars locked in gravitational embrace. Wider still are detached binaries, where both stars remain well within their Roche lobes and evolve almost independently, connected only by their mutual orbit. The bright star, Sirius, the most luminous star in Earth's night sky at a distance of 8.6 light-years, belongs to this category. Sirius A, a white main-sequence star twice as massive as the Sun and 25 times more luminous, is accompanied by Sirius B, a white dwarf roughly the size of Earth but containing nearly the mass of the Sun. The two orbit each other every 50 years at distances ranging from 8 to 31 astronomical units. Sirius B represents the evolutionary future of Sirius A, the dense core left behind after a star exhausts its nuclear fuel and sheds its outer layers. In this system, the past and future of stellar evolution orbit together, a gravitational archive of stellar life cycles. The orbital mechanics of binary stars follow Kepler's laws with elegant precision, but the presence of two massive bodies introduces complexities absent in planetary systems. The center of mass around which both stars orbit, called the barycenter, lies not at the center of either star, but at a point determined by their relative masses. For equal mass binaries, the barycenter sits exactly midway between them. For unequal pairs like Sirius, it lies closer to the more massive component. Both stars trace elliptical paths around this invisible pivot point, their orbital periods identical, their velocities inversely proportional to their masses. A star twice as massive as its companion moves at half the speed, maintaining the gravitational balance that keeps the system stable. These orbital dances produce measurable effects that allow astronomers to weigh stars with remarkable precision. As binary components orbit, they alternately approach and recede from Earth, causing Doppler shifts in their spectral lines. The star moving toward us shows light shifted slightly toward blue wavelengths, while the receding star shows red shifted light. By measuring these velocity variations over time, astronomers can determine orbital periods, eccentricities, and the ratio of stellar masses. If the orbital plane aligns with our line of sight, the stars periodically eclipse each other, providing additional information about their sizes and surface temperatures. The combination of spectroscopic and photometric observations yields stellar masses accurate to within a few percent, the most reliable mass measurements in all of astronomy. Multiple star systems add layers of gravitational complexity. Triple systems, like Alpha Centauri, our nearest stellar neighbor at 4.37 light-years, typically organize themselves hierarchically. Alpha Centauri A and B, both Sun-like stars, orbit each other every 80 years at distances ranging from 11 to 36 astronomical units. The third component, Proxima Centauri, a dim red dwarf, orbits this central pair at a distance of roughly 13,000 astronomical units, taking approximately 550,000 years to complete one circuit. This hierarchical arrangement, a tight inner pair orbited by a distant third body, represents the stable configuration that allows multiple star systems to persist for billions of years without gravitational chaos ejecting members into interstellar space. Quadruple systems extend this hierarchy further. The star system HD 98800, located 150 light-years away in the constellation Crater, contains 4 stars arranged as 2 binary pairs orbiting each other. Each inner pair completes its orbit in roughly 1 year, while the 2 pairs circle their common center of mass over a period of approximately 300 years. The gravitational interactions between these 4 stars create complex orbital perturbations, yet the system remains stable because the hierarchy maintains sufficient separation between gravitational influences. The record for stellar multiplicity belongs to systems like Nu Scorpii and AR Cassiopeiae, each containing 7 confirmed stellar components arranged in nested hierarchical configurations. These systems resemble gravitational matryoshka dolls, with binary pairs orbiting other binary pairs, all bound together by the invisible architecture of gravity. The outermost orbits in such systems may take hundreds of thousands of years to complete, while the innermost pairs whirl around each other in days or weeks. Binary and multiple star systems profoundly influence stellar evolution. Mass transfer between close companions can rejuvenate aging stars, adding fresh hydrogen fuel to cores that would otherwise exhaust their supplies. This process explains the existence of blue stragglers, stars in old clusters that appear too young and too blue for their surroundings. They have been revitalized by mass donated from binary companions, their clocks reset by gravitational generosity. Conversely, mass transfer can strip stars of their outer layers, exposing hot cores that would normally remain hidden beneath thick envelopes of gas. The most dramatic consequences of binary evolution occur when one component reaches the end of its life. If a white dwarf in a close binary accretes enough material from its companion to exceed 1.4 solar masses, the Chandrasekhar limit, it cannot support itself against gravitational collapse. The result is a Type Ia supernova, a thermonuclear explosion that completely destroys the white dwarf and briefly outshines its entire host galaxy. These explosions release remarkably consistent amounts of energy, making them valuable distance indicators for measuring cosmic expansion. Every Type Ia supernova represents the death of a binary system, the final act in a gravitational partnership that may have lasted billions of years. Neutron stars in binaries produce different phenomena. As matter streams onto a neutron star's surface, it releases enormous energy, heating to temperatures exceeding 10 million Kelvin and emitting powerful X-rays. These X-ray binaries rank among the brightest sources in the X-ray sky, their luminosities sometimes exceeding 100,000 times the Sun's total output across all wavelengths. The neutron star's intense magnetic field channels infalling material onto its magnetic poles, creating hot spots that sweep across our line of sight as the star rotates, producing regular pulses of radiation. When 2 neutron stars orbit each other in a tight binary, gravitational wave emission gradually drains energy from their orbit, causing them to spiral inward over millions of years. The binary pulsar PSRB 1913+16, discovered in 1974 at a distance of 21,000 light-years, provided the first indirect evidence for gravitational waves. Its orbital period decreases by approximately 76 microseconds per year. exactly matching the predictions of general relativity for energy loss through gravitational radiation. Eventually, such systems merge in cataclysmic collisions that produce short gamma-ray bursts and forge heavy elements like gold and platinum in the neutron-rich debris. Beyond these dramatic endpoints, binary stars serve as cosmic laboratories for testing stellar physics. The precise masses obtainable from binary orbits anchor our understanding of how stellar properties relate to each other. The mass-luminosity relationship, which describes how a star's brightness depends on its mass, derives primarily from observations of binary systems. Without binaries, stellar astrophysics would rest on far shakier foundations. Yet not all stellar companions achieved their status through nuclear fusion. Between the realm of the smallest stars and the largest planets exists a category of objects that blur the boundary between these classifications. Bodies too massive to be planets, but too small to sustain hydrogen fusion in their cores. These curious objects, the brown dwarfs, occupy a twilight zone in the cosmic classification of matter. They form in precisely the same manner as true stars, from the gravitational collapse of dense cores within molecular clouds. Yet they never quite achieve the defining characteristic of stellar existence. Their masses, ranging from approximately 13 to 80 times that of Jupiter, place them in a peculiar intermediate state. Too massive to be planets, which form through the gradual accumulation of material in protoplanetary disks, yet too small to sustain the proton-proton chain reaction that powers main-sequence stars like our Sun. The critical threshold lies at roughly 0.075 solar masses, or about 75 Jupiter masses. Below this limit, the core of a collapsing gas cloud never reaches the temperature of approximately 10 million Kelvin required to fuse hydrogen nuclei into helium at a sustainable rate. The object contracts, heats up, glows with the energy of its gravitational compression, but cannot ignite the nuclear furnace that would stabilize it against further collapse. It becomes a brown dwarf, a body that shines not through fusion, but through the slow release of gravitational potential energy, gradually cooling over billions of years like an ember fading in the darkness. The first confirmed brown dwarf, Gliese 229b, was discovered in 1995, orbiting a red dwarf star approximately 19 light-years from Earth. Its surface temperature of roughly 950 Kelvin, cooler than many industrial furnaces, immediately distinguished it from true stars. The detection of methane in its atmosphere, a molecule that cannot exist in the searing photospheres of hydrogen-burning stars, provided definitive evidence of its substellar nature. Since that initial discovery, astronomers have catalogued thousands of brown dwarfs, revealing a population that may rival the number of main-sequence stars in our galaxy. The spectral classification system, which organizes stars by their surface temperatures and atmospheric compositions, required expansion to accommodate these objects. Beyond the familiar sequence of O, B, A, F, G, K, and M-type stars, astronomers added 3 new categories: L, T, and Y dwarfs. L dwarfs, with surface temperatures between roughly 1,300 and 2,200 Kelvin, show atmospheres dominated by metal hydrides and alkali metals. Their spectra reveal the presence of iron hydride, chromium hydride, and neutral potassium and sodium, elements that would be ionized or bound into different molecules in hotter stellar atmospheres. T-dwarfs represent a cooler regime, with temperatures spanning approximately 550 to 1,300 Kelvin. Methane becomes the dominant carbon-bearing molecule in these atmospheres, absorbing infrared light in distinctive patterns that make T-dwarfs appear remarkably blue in certain wavelength comparisons. Water vapor also features prominently in their spectra, condensing into clouds at higher altitudes while remaining gaseous in the deeper, warmer layers. The transition from L to T spectral types occurs rapidly, suggesting that atmospheric dynamics undergo dramatic changes as brown dwarfs cool through this temperature range. The coldest known brown dwarfs belong to the Y spectral class, with surface temperatures that can drop below 300 Kelvin, cooler than a summer day on Earth. Y0855-0714, discovered in 2014 at a distance of only 7.2 light-years, holds the record for the coldest known brown dwarf, with an estimated temperature of approximately 250 Kelvin, or roughly minus 23 degrees Celsius. At such temperatures, water ice clouds form in the upper atmosphere, and the object emits almost no visible light, detectable only through its faint infrared glow. If placed in our solar system, this brown dwarf would appear dimmer than many asteroids, despite containing several times Jupiter's mass. The internal structure of brown dwarfs differs fundamentally from both planets and stars. Unlike Jupiter, whose interior consists of metallic hydrogen surrounding a dense core of heavier elements, brown dwarfs are fully convective throughout most of their evolution. Heat generated in the deep interior rises directly to the surface through churning convection currents, rather than being transported by radiation as in the cores of sun-like stars. This convective mixing ensures that brown dwarfs maintain relatively uniform chemical compositions from center to surface, with no stratification into distinct layers. The physics governing brown dwarf interiors involves electron degeneracy pressure, the same quantum mechanical effect that supports white dwarf stars against gravitational collapse. As matter compresses to extreme densities, the Pauli exclusion principle prevents electrons from occupying identical quantum states, creating an outward pressure that resists further compression regardless of temperature. In brown dwarfs, this degeneracy pressure becomes significant before core temperatures reach the hydrogen fusion threshold, halting contraction and preventing the object from ever becoming a true star. A peculiar consequence of this physics is that all brown dwarfs share approximately the same radius, regardless of their mass. Whether containing 15 Jupiter masses or 70, a brown dwarf measures roughly the same size as Jupiter itself, about 140,000 kilometers in diameter. Adding more mass simply increases the internal density and degeneracy pressure without significantly expanding the object. This mass-radius relationship distinguishes brown dwarfs from both planets, which grow larger with increasing mass, and main sequence stars, which also expand with greater mass. Although brown dwarfs cannot sustain hydrogen fusion, the most massive examples briefly ignite deuterium in their cores during their youth. Deuterium, the heavy isotope of hydrogen containing one proton and one neutron, fuses at lower temperatures than ordinary hydrogen, approximately 1 million Kelvin rather than 10 million. Objects above roughly 13 Jupiter masses achieve this threshold during their initial contraction, burning through their deuterium supply over a few 100 million years. This brief nuclear episode slows their cooling, but does not fundamentally alter their fate. Once the deuterium exhausts, they resume their gradual thermal decline. The boundary between brown dwarfs and giant planets remains somewhat ambiguous, defined more by formation mechanism than by any sharp physical transition. Objects that form through gravitational collapse of gas clouds, like stars, are classified as brown dwarfs regardless of their mass. Objects that form through core accretion in protoplanetary disks, building up from solid particles that then capture gaseous envelopes, are classified as planets. Yet distinguishing these formation pathways for any individual object proves challenging, particularly for free-floating objects discovered drifting through interstellar space without any host star. Surveys of young star-forming regions have revealed populations of isolated objects with masses below the deuterium-burning limit, sometimes called planetary mass objects or sub-brown dwarfs. The Sigma Orionis cluster, located approximately 1,150 light-years away, contains dozens of such objects with estimated masses between 5 and 13 Jupiter masses. Whether these formed like stars through direct collapse or were ejected from planetary systems through gravitational interactions remains unclear. Their existence blurs the conceptual boundary between the smallest products of stellar formation and the largest products of planetary formation. Brown dwarfs exhibit weather patterns far more dramatic than any planet in our solar system. Infrared observations reveal brightness variations over periods of hours, indicating that their surfaces are mottled with features analogous to storms and cloud bands. The brown dwarf Lumen 16b, one of the closest brown dwarfs to Earth at only 6.5 light-years distant, shows brightness fluctuations of several percent as it rotates with a period of approximately 5 hours. Doppler imaging techniques have mapped its surface, revealing a patchy distribution of thick and thin clouds, with clearings that expose hotter, deeper atmospheric layers. The atmospheric chemistry of brown dwarfs includes exotic compounds rarely encountered elsewhere. Silicate clouds, composed of minerals like enstatite and forsterite, form in the atmospheres of warmer L dwarfs, raining liquid rock into the deeper layers. Iron and other refractory metals condense into clouds at similar temperatures. As brown dwarfs cool into the T and Y spectral classes, these silicate clouds sink below the visible photosphere, replaced by clouds of sodium sulfide, potassium chloride, and eventually water ice and ammonia. The cooling timescales of brown dwarfs span billions of years, making their temperatures sensitive indicators of their ages. A brown dwarf of 50 Jupiter masses begins its life with a surface temperature exceeding 2,500 Kelvin, appearing as a dim red object, barely distinguishable from the faintest true stars. After 1 billion years, it cools to roughly 1,500 Kelvin. After 10 billion years, it reaches approximately 500 Kelvin. Given enough time, all brown dwarfs will eventually cool to temperatures indistinguishable from the cosmic microwave background, becoming essentially invisible. dark, Jupiter-sized objects drifting through the galaxy, detectable only through their gravitational influence. These failed stars, these oversized planets, populate the galaxy in numbers that astronomers are only beginning to appreciate. For every sun-like star, there may be several brown dwarfs lurking in the darkness, their feeble infrared glow escaping detection by all but the most sensitive instruments. They represent a vast reservoir of matter that never achieved stellar ignition, a population of objects frozen in a permanent state of almost starhood. Yet even true stars do not burn forever. The nuclear reactions that power them eventually exhaust their fuel, leaving behind remnants that compress matter to densities and states unknown on any planet or brown dwarf, the endpoints of stellar evolution that transform ordinary matter into something far stranger. When a star exhausts the hydrogen fuel in its core, the balance that sustained it for millions or billions of years finally tips. The outward pressure of nuclear fusion, which had held gravity at bay throughout the star's life, begins to falter. What happens next depends almost entirely on one factor: mass. This single number, how much matter the star accumulated during its formation, determines whether it will fade gently into a dense crystalline sphere, collapse into an object so compressed that a teaspoon would weigh billions of tons, or vanish entirely behind an event horizon from which nothing, not even light, can escape. For stars like the Sun, with masses below roughly 8 times solar, the end comes gradually. As hydrogen fusion ceases in the core, the star contracts and heats until helium begins fusing into carbon and oxygen. The outer layers expand enormously, creating a red giant that may swell to engulf any inner planets. Our own Sun will one day expand past the current orbit of Venus, perhaps reaching Earth itself. But this giant phase cannot last. Within a few 100 million years, the outer layers drift away as a planetary nebula, a shell of glowing gas illuminated by the hot core within, while that core, now exposed, begins its long transformation into a white dwarf. A white dwarf is the compressed remnant of what was once a star's nuclear furnace. Containing roughly the mass of the Sun packed into a sphere approximately the size of Earth, about 12,700 kilometers in diameter, these objects achieve densities of around 1 million grams per cubic centimeter. A sugar cube-sized sample of white dwarf material would weigh approximately 1 ton on Earth's surface. This extraordinary compression occurs because the star's matter has been squeezed until electrons are forced into their lowest possible energy states, creating a quantum mechanical pressure called electron degeneracy that resists further collapse. The white dwarf Sirius B, companion to the brightest star in Earth's night sky, illustrates these extremes perfectly. Despite containing nearly the same mass as the Sun, Sirius B measures only about 11,800 kilometers across. Smaller than Earth. Its surface temperature exceeds 25,000 Kelvin, making it far hotter than the Sun, yet its total luminosity is less than 3% of solar because of its tiny radiating area. This intense heat represents the residual thermal energy from the star's active phase, energy that will slowly radiate away over billions of years. White dwarfs cool like embers removed from a fire, but the timescale stretches beyond comprehension. A white dwarf requires roughly 4 billion years to cool from its initial temperature of over 100,000 Kelvin down to about 8,000 Kelvin. To cool further to temperatures below 4,000 Kelvin, where it would appear distinctly red, requires additional tens of billions of years. The universe itself, at 13.8 billion years old, has not existed long enough for any white dwarf to cool completely into a theoretical black dwarf, a cold, dark sphere radiating nothing detectable. Every white dwarf that has ever formed still glows with residual heat. The composition of white dwarfs reflects their stellar ancestry. Most consist primarily of carbon and oxygen, the products of helium fusion in their progenitor stars. Some, formed from lower mass stars that never achieved helium ignition, contain mostly helium. The most massive white dwarfs, approaching the Chandrasekhar limit of approximately 1.4 solar masses, may contain oxygen, neon, and magnesium in their cores. Beyond this mass limit, electron degeneracy pressure cannot support the star against gravity, and collapse becomes inevitable. When stars more massive than about 8 solar masses reach the end of their nuclear burning, they face a more violent fate. These stellar giants progress through successive fusion stages: hydrogen to helium, helium to carbon, carbon to neon, neon to oxygen, oxygen to silicon, each stage shorter than the last. Silicon fusion, the final stage, produces iron in the core and lasts merely days. Iron represents a dead end for fusion. Combining iron nuclei consumes energy rather than releasing it. When the iron core grows beyond approximately 1.4 solar masses, electron degeneracy pressure fails catastrophically. The core collapses at velocities approaching 70,000 kilometers per second, nearly a quarter of the speed of light. In less than a second, a region the size of Earth compresses to a sphere roughly 20 kilometers across. Protons and electrons merge into neutrons, releasing a flood of neutrinos so intense that despite their ghostly nature, they carry away 99% of the collapse energy. The outer layers of the star, falling inward, bounce off this suddenly rigid neutron core and explode outward as a supernova, briefly outshining entire galaxies with luminosities reaching 10 billion times that of the Sun. What remains at the center is a neutron star, an object of almost incomprehensible density. A typical neutron star contains between 1.4 and 2 solar masses, compressed into a sphere measuring only about 20 kilometers in diameter. The density reaches 400 trillion grams per cubic centimeter, roughly the density of an atomic nucleus extended to macroscopic scales. A single teaspoon of neutron star material would weigh approximately 6 billion tons, equivalent to a mountain compressed into a thimble. The surface gravity of a neutron star exceeds 200 billion times Earth's gravity. An object falling from 1 meter above the surface would impact at roughly 2,000 kilometers per second. The escape velocity approaches 200,000 kilometers per second, more than half the speed of light. Light itself, climbing away from a neutron star, loses roughly 30% of its energy to gravitational redshift. Neutron stars rotate with extraordinary speed, a consequence of angular momentum conservation during collapse. A slowly rotating stellar core, spinning once per month, compresses into a neutron star spinning hundreds of times per second. The Crab pulsar, remnant of a supernova observed in the year 1054, rotates approximately 30 times per second. The fastest known pulsar, PSRJ 1748-2446 AD, spins at 716 rotations per second, its equator moving at roughly 24% of light speed. These rotating neutron stars emit beams of radiation from their magnetic poles, which may not align with their rotation axes. As the star spins, these beams sweep through space like lighthouse beacons. When one beam happens to cross Earth's line of sight, we detect regular pulses of radio waves, X-rays, or gamma rays, hence the name pulsar. The regularity of these pulses rivals atomic clocks. Some millisecond pulses maintain timing stability to within 1 part in 10 to the 15th power over years of observation. The magnetic fields of neutron stars dwarf anything else in the universe. Typical neutron stars possess fields of 100 million to 1 trillion Tesla, compared to Earth's field of roughly 50 microtesla. Magnetas, a subset of neutron stars with the strongest known magnetic fields, reach 100 billion to 1 quadrillion Tesla. At such field strengths, the vacuum itself becomes birefringent, bending light differently depending on its polarization. The magnetic field energy of a magnetar exceeds the total energy output of the Sun over 10,000 years. Yet even neutron degeneracy pressure has limits. When the collapsing core of a massive star exceeds roughly 3 solar masses, the Tolman-Oppenheimer-Volkoff limit, no known force can halt the collapse. The matter continues compressing past neutron star densities, past any state physics can describe with certainty, until it vanishes behind an event horizon. A black hole has formed. The event horizon is not a physical surface, but a mathematical boundary, the radius at which escape velocity equals the speed of light. For a black hole of 10 solar masses, this Schwarzschild radius measures approximately 30 kilometers. Nothing that crosses this boundary can return. Information, matter, and light all fall inexorably toward the central singularity, where density becomes infinite and known physics breaks down. Stellar mass black holes formed from collapsed massive stars typically range from about 5 to several tens of solar masses. The black hole in the binary system Cygnus X1, one of the first confirmed black holes, contains approximately 21 solar masses. The merger of 2 black holes detected by gravitational wave observatories in 2015 involved objects of 36 and 29 solar masses, producing a final black hole of 62 solar masses, with 3 solar masses of energy radiated as gravitational waves in a fraction of a second. These stellar remnants, white dwarfs, neutron stars, and black holes, represent matter in its most extreme configurations, pushed to densities and conditions impossible to replicate in any laboratory. They are the endpoints of stellar evolution, the final forms that stars assume when their nuclear fires extinguish. Scattered throughout every galaxy, they accumulate over cosmic time, each one a memorial to a star that once burned bright. Yet stars and their remnants do not exist in isolation within galaxies. They orbit through vast spaces filled with gas and dust, regions where new stars form and old stars shed their outer layers. Beyond our own solar system, beyond even the nearest stars, lie countless other worlds orbiting distant suns. planets that may bear no resemblance to anything in our own cosmic neighborhood. Those distant worlds, orbiting stars scattered across the galaxy, remained hidden from human knowledge until remarkably recently. For most of history, the existence of planets beyond our solar system was pure speculation, a philosophical question rather than a scientific one. The ancient Greeks debated whether other worlds might exist around distant stars, but they possessed no means to detect them. Even as telescopes grew more powerful through the centuries, revealing the moons of Jupiter and the rings of Saturn in exquisite detail, planets orbiting other stars remained utterly invisible, lost in the overwhelming glare of their parent suns. The challenge is one of contrast and distance. A typical star outshines any planet orbiting it by factors of millions to billions. Jupiter, the largest planet in our solar system, reflects only about 1/billionth the light that the Sun produces. From the distance of even the nearest star, Proxima Centauri at 4.24 light-years away, detecting Jupiter's faint reflected glow against the Sun's brilliance would be like trying to spot a firefly hovering next to a lighthouse from thousands of kilometers away. The planet's light simply drowns in stellar radiance, yet planets betray their presence through subtler means. As a planet orbits its star, its gravitational pull tugs the star in a tiny counter-orbit around their shared center of mass. The star does not remain perfectly stationary while the planet circles it. Instead, both bodies orbit a common point, like two dancers holding hands and spinning together, though one dancer is vastly more massive than the other. For our own Sun, Jupiter's gravitational influence causes a wobble of about 12 meters per second over Jupiter's 12-year orbital period. This motion, though minuscule compared to the Sun's diameter of 1.4 million kilometers, shifts the wavelengths of the star's light in detectable ways through the Doppler effect. In 1995, Swiss astronomers Michel Mayer and Didier Queloz detected exactly this kind of wobble in the star 51 Pegasi, located 50 light-years away in the constellation Pegasus. The wobble revealed a planet with at least half the mass of Jupiter, but orbiting its star in just 4.2 days, meaning it circled closer to its Sun than Mercury orbits ours. This discovery, which would earn Mayer and Queloz the Nobel Prize in Physics in 2019, shattered assumptions about planetary systems. Astronomers had expected other systems to resemble our own, with small rocky planets close to their stars and gas giants in distant, slow orbits. Instead, the first confirmed exoplanet around a Sun-like star was a massive world baked by stellar radiation at temperatures exceeding 1,000 degrees Celsius. The radial velocity method, as this wobble detection technique is called, opened the floodgates. Within a decade, astronomers had confirmed dozens of exoplanets, then hundreds. But another method would prove even more prolific. When a planet passes directly between its star and Earth, an event called a transit, it blocks a tiny fraction of the star's light. For a Jupiter-sized planet crossing a Sun-sized star, this dimming amounts to about 1%. For an Earth-sized planet, the dimming is just 0.0084%, or 84 parts per million. Detecting such minute variations requires extraordinary precision, but space-based telescopes, free from the blurring effects of Earth's atmosphere, proved capable of exactly this sensitivity. NASA's Kepler Space Telescope, launched in 2009, stared at a single patch of sky containing about 150,000 stars for nearly 4 years, watching for the telltale dips in brightness that signal transiting planets. The results transformed our understanding of planetary abundance. Kepler detected over 2,600 confirmed exoplanets before its primary mission ended, with thousands more candidates awaiting verification. Statistical analysis of Kepler's data suggested that, on average, every star in the Milky Way hosts at least one planet. With roughly 200 to 400 billion stars in our galaxy, this implies hundreds of billions of worlds orbiting within the Milky Way alone. The diversity of these worlds defies easy categorization. Hot Jupiters like 51 Pegasi b represent just one extreme. At the other end lie super-Earths, planets with masses between 1 and 10 times Earth's mass, a category entirely absent from our own solar system. Kepler 442b, orbiting a star 112 light-years away, has a mass roughly 2.3 times Earth's and receives about 70% of the light that Earth receives from the Sun, placing it within its star's habitable zone, where liquid water could potentially exist on its surface. Its year lasts 112 Earth days, and its equilibrium temperature, assuming an Earth-like atmosphere, would hover around -40 degrees Celsius. Cold, but not impossibly so for liquid water to persist. Mini-Neptunes occupy another unexpected niche, with radii between 1.7 and 3.5 times Earth's radius. These worlds appear to possess thick hydrogen-helium atmospheres surrounding rocky or icy cores, representing a planetary type with no solar system analog. Kepler's data revealed that mini-Neptunes are among the most common planets in the galaxy, more abundant than both Earth-sized worlds and Jupiter-sized giants. Their prevalence raises questions about planetary formation that astronomers are still working to answer. Some exoplanets orbit in configurations that seem almost impossible. Kepler 16b, located 245 light-years away, orbits 2 stars simultaneously. A circumbinary planet where the sky would display 2 suns rising and setting in complex patterns. The 2 stars orbit each other every 41 days, while the planet circles both of them every 229 days, at a distance of about 104 million kilometers. Despite the gravitational complexity of such a system, the planet's orbit remains stable, maintained by precise resonances between all 3 bodies. The TRAPPIST-1 system, discovered in 2017, presents perhaps the most remarkable planetary architecture yet found. This ultra-cool red dwarf star, just 40 light-years away and only 9% the mass of our Sun, hosts 7 Earth-sized planets packed into orbits closer than Mercury's distance from the Sun. The outermost planet, TRAPPIST-1H, orbits at just 9.2 million kilometers from its star, completing 1 orbit every 19 days. 3 of these worlds, TRAPPIST-1, E, F, and G, orbit within the star's habitable zone, where temperatures might permit liquid water. The planets are locked in a chain of orbital resonances, with their periods forming simple ratios. For every 2 orbits of the outermost planet, the next inner planet completes 3, and so on inward. This gravitational choreography keeps the system stable, despite the crowded orbital space. Direct imaging of exoplanets remains extraordinarily difficult, but advances in coronagraph technology, instruments that block a star's light while allowing planetary light to pass, have enabled photographs of a handful of worlds. The HR 8799 system, 129 light-years away, contains 4 giant planets that have been directly imaged, each several times Jupiter's mass, orbiting at distances of 15 to 70 astronomical units from their star. These worlds glow in infrared light, still radiating the heat of their formation roughly 30 million years ago. Their temperatures range from about 800 to 1100 Kelvin, hot enough to vaporize iron. Spectroscopy, the analysis of light passing through or reflected from planetary atmospheres, has begun revealing the chemical compositions of exoplanet atmospheres. When a planet transits its star, some starlight filters through the planet's atmosphere before reaching Earth. Different molecules absorb light at characteristic wavelengths, leaving fingerprints in the spectrum. Water vapor has been detected in the atmospheres of several hot Jupiters, along with sodium, potassium, and even titanium oxide. The James Webb Space Telescope, with its unprecedented infrared sensitivity, has detected carbon dioxide in the atmosphere of WASP 39b, a hot Jupiter 700 light-years away, and has begun characterizing the atmospheres of smaller, cooler worlds. The search for biosignatures, atmospheric chemicals that might indicate biological activity, drives much of exoplanet research. On Earth, oxygen accumulates in the atmosphere primarily through photosynthesis, while methane is produced largely by living organisms. The simultaneous presence of both gases, which would normally react and neutralize each other, suggests continuous replenishment by life. Detecting such chemical disequilibrium in an exoplanet atmosphere would constitute compelling, though not conclusive, evidence for extraterrestrial biology. Yet the sheer number of worlds now known to exist transforms the question of life elsewhere from philosophical speculation into statistical probability. If even a tiny fraction of the billions of planets in our galaxy harbor conditions suitable for life, the universe may teem with biology in forms we cannot yet imagine. These countless worlds, each following its own orbital path around its own stellar furnace, represent the building blocks of something larger. The stellar populations that together constitute the visible matter of galaxies themselves. Between those countless stars and their orbiting worlds stretches something that appears, at first glance, to be emptiness. Yet this apparent void contains the raw material from which all stars are born and to which many will eventually return. These vast clouds of gas and dust, the nebulae, represent both the nurseries and the graveyards of stellar evolution, immense structures spanning dozens or even hundreds of light years, containing enough matter to birth thousands of suns. The word nebula itself comes from the Latin for cloud or mist, and early astronomers who observed these faint, fuzzy patches through primitive telescopes could not have imagined their true nature. What appeared as smudges of light against the dark sky are in fact structures of staggering scale. The Orion Nebula, visible to the naked eye as a hazy spot in the sword of the constellation Orion, spans approximately 24 light-years across, a distance so vast that light itself requires nearly a quarter century to traverse it. Yet this famous nebula represents merely a small illuminated cavity within a far larger molecular cloud complex that extends across hundreds of light years and contains enough hydrogen to form tens of thousands of stars like our Sun. These stellar nurseries, the emission nebulae, glow with their own light, rather than merely reflecting the light of nearby stars. The mechanism behind this luminescence involves the same atomic physics that powers neon signs on Earth, though operating on scales billions of times larger. Young hot stars embedded within the cloud emit intense ultraviolet radiation, with surface temperatures often exceeding 30,000 Kelvin. This energetic light strips electrons from hydrogen atoms in the surrounding gas, ionizing the nebula. When these freed electrons recombine with hydrogen nuclei, they cascade down through energy levels, releasing photons at specific wavelengths. The characteristic red glow of many emission nebulae comes from hydrogen alpha emission at 656.3 nanometers, produced when electrons fall from the third to the second energy level of hydrogen atoms. The density within these glowing clouds varies enormously, but remains extraordinarily low by terrestrial standards. A typical emission nebula contains perhaps 100 to 10,000 particles per cubic centimeter, a vacuum far more perfect than anything achievable in laboratories on Earth, where even the best vacuum chambers contain billions of molecules per cubic centimeter. Yet across the immense volumes involved, this tenuous gas accumulates into substantial mass. The Carina Nebula, one of the largest and brightest in the Milky Way, contains an estimated 900,000 solar masses of material spread across a region roughly 460 light-years in diameter. Temperature within nebulae spans an enormous range depending on proximity to heating sources. The ionized regions surrounding hot young stars reach temperatures of 8,000 to 12,000 Kelvin, hot enough that atoms move at speeds of several kilometers per second. Yet in the dense molecular cores shielded from stellar radiation, temperatures plummet to merely 10 to 20 Kelvin, colder than any natural environment on Earth, colder even than the surface of Pluto. At these frigid temperatures, hydrogen atoms bond into molecules, and more complex chemistry becomes possible. Radio telescopes have detected over 200 different molecular species in these cold cores, including water, ammonia, methanol, and even amino acids, the building blocks of proteins. The process by which these diffuse clouds collapse to form stars requires overcoming the natural tendency of gas to expand. Thermal pressure pushes outward, resisting compression, while magnetic fields threading through the cloud provide additional support against gravity. For collapse to begin, something must tip the balance. The shock wave from a nearby supernova can compress a region of the cloud, increasing its density until gravity overwhelms the opposing forces. Similarly, the spiral density waves that create a galaxy's arms can squeeze molecular clouds as they pass through, triggering cascades of star formation. Once collapse begins in one region, the radiation and stellar winds from newly formed stars can compress adjacent areas, propagating star formation through the cloud like a slow-motion chain reaction spanning millions of years. Not all nebulae represent sites of creation. Some mark the opposite end of stellar existence, the expanding shells of gas expelled by dying stars. Planetary nebulae, despite their misleading name, have nothing to do with planets. Early astronomers observing these round, greenish objects through small telescopes thought they resembled the disks of distant planets, and the name persisted long after their true nature became understood. These structures form when stars similar to our Sun exhaust their nuclear fuel and shed their outer layers into space. The exposed stellar core, now a white dwarf with surface temperatures reaching 100,000 Kelvin or more, ionizes this expelled material, causing it to glow. The Ring Nebula in the constellation Lyra provides a classic example, appearing as a cosmic smoke ring approximately 1 light-year in diameter. The central white dwarf, visible as a faint point at the nebula's center, has a surface temperature of roughly 120,000 Kelvin and a luminosity 200 times that of our Sun, though most of this energy emerges as ultraviolet radiation invisible to human eyes. The nebula itself expands at approximately 20 kilometers per second, meaning the entire structure will dissipate into the interstellar medium within perhaps 20,000 years, a brief moment in cosmic time. Far more violent are the supernova remnants, the expanding debris fields left behind when massive stars end their lives in catastrophic explosions. The Crab Nebula in Taurus represents the remains of a supernova observed by Chinese astronomers in the year 1054 CE. Nearly 1,000 years later, this remnant spans approximately 11 light-years and continues expanding at roughly 1,500 kilometers per second. At its center spins a neutron star, the collapsed core of the original star, rotating 30 times per second and emitting beams of radiation that sweep across Earth like a cosmic lighthouse. The filaments of the Crab Nebula glow with the light of ionized hydrogen, helium, carbon, oxygen, and heavier elements forged in the original star and scattered across space by the explosion. These supernova remnants serve a crucial function in cosmic chemistry. The explosion that creates them also synthesizes elements heavier than iron through rapid neutron capture, producing gold, platinum, uranium, and other heavy nuclei that cannot form through normal stellar fusion. As the remnant expands and eventually merges with the surrounding interstellar medium, it enriches the gas from which future generations of stars will form. The iron in human blood, the calcium in bones, the oxygen we breathe, all were forged in stars and distributed through space by nebulae like these. Reflection nebulae present yet another category, clouds that shine not through their own emission but by scattering the light of nearby stars. The Pleiades star cluster, visible in the winter sky, is surrounded by wispy blue nebulosity that represents interstellar dust illuminated by the cluster's hot blue stars. The blue color arises because dust particles scatter shorter wavelengths of light more efficiently than longer ones, the same Rayleigh scattering that makes Earth's sky blue. These reflection nebulae often appear adjacent to emission nebulae, with the reflection component visible where the gas is too cool or too distant from ionizing stars to emit its own light. Dark nebulae represent perhaps the most mysterious-looking of all, appearing as inky black patches against the background glow of the Milky Way. The Coalsack Nebula near the Southern Cross and the Horsehead Nebula in Orion exemplify these structures. Dense concentrations of dust and cold molecular gas that block the light of more distant stars. The Horsehead itself, a pillar of obscuring material silhouetted against the glow of an emission nebula behind it, contains enough material to form perhaps 5 stars the mass of our Sun. Within such dark clouds, shielded from the disruptive radiation of nearby stars, the slow process of gravitational collapse proceeds, preparing the next generation of stellar birth. The dust that makes these dark nebulae opaque consists not of the household dust familiar on Earth, but of microscopic grains of silicates and carbonaceous material, each typically less than a micrometer in diameter. These grains form in the outer atmospheres of aging stars, particularly red giants and asymptotic giant branch stars, where temperatures are cool enough for refractory materials to condense from the stellar wind. Stellar winds carry these grains into interstellar space, where they accumulate over billions of years. Though dust constitutes only about 1% of the mass of the interstellar medium, with gas comprising the remaining 99%, its effect on light is profound. A dense molecular cloud can reduce the brightness of background stars by factors of millions, rendering entire regions of the galaxy invisible at optical wavelengths. The interplay between these various types of nebulae creates a cosmic cycle of matter. Molecular clouds collapse to form stars, which live out their nuclear burning lives before returning much of their mass to space through stellar winds, planetary nebulae, or supernova explosions. This enriched material mixes with the surrounding interstellar medium, eventually becoming incorporated into new molecular clouds where the cycle begins again. Each generation of stars contains a slightly higher proportion of heavy elements than the last, a gradual enrichment that has transformed the chemistry of the universe over 13 billion years. Within our own galaxy, nebulae concentrate along the spiral arms where density waves compress the interstellar medium and trigger star formation. The Sagittarius arm, the Scutum Centaurus arm, and our own Orion Spur all contain numerous emission nebulae marking regions of active stellar birth. These glowing clouds trace the galaxy's spiral structure like luminous beads on invisible threads, their distribution revealing the underlying gravitational dynamics that shape the Milky Way. Yet nebulae represent only the most visible component of a far more extensive medium that fills the space between all stars, a tenuous but crucial reservoir of matter that connects stellar populations across the entire galactic disk. From those luminous nebulae, where gravity has compressed hydrogen and helium into dense knots of collapsing gas, emerge not solitary stars, but entire families born together. These open star clusters represent the immediate products of stellar nurseries, groups of dozens to several thousand stars that share a common origin, moving through space as gravitational siblings. They are among the youngest structures in the galaxy, their ages measured in mere millions of years rather than the billions that characterize older stellar populations. The process begins within the densest cores of molecular clouds, where a single triggering event, perhaps a nearby supernova shockwave or the passage of a spiral density wave, initiates collapse across a region spanning several light years. As the cloud fragments, multiple cores contract simultaneously, each destined to become a star. Because they form from the same parent cloud, these stars share nearly identical chemical compositions, their atmospheres containing the same ratios of iron to hydrogen, oxygen to carbon, magnesium to silicon. This chemical fingerprint becomes a permanent marker of their shared heritage, allowing astronomers to identify cluster members even after they have drifted apart over millions of years. The Pleiades, perhaps the most famous open cluster visible to the naked eye, illustrates this stellar kinship beautifully. Located approximately 444 light-years from Earth in the constellation Taurus, this cluster contains over 1,000 confirmed members, though only the brightest 6 or 7 stars are visible without optical aid. The cluster spans roughly 17 light-years in diameter, with its hot blue stars, the brightest of which, Alcyone, shines with a luminosity 2,400 times that of the Sun, dominating the visual appearance. At an age of approximately 100 million years, the Pleiades represents a relatively young cluster, its most massive members still burning hydrogen in their cores, while the surrounding wisps of reflection nebulae hint at the molecular cloud from which they emerged. The stellar density within open clusters varies considerably, but typically ranges from 0.1 to 10 stars per cubic parsec near the cluster center. This concentration, while far greater than the average stellar density in the solar neighborhood, approximately 0.14 stars per cubic parsec, remains modest compared to the extreme crowding found in other stellar groupings. The average separation between stars in a typical open cluster measures roughly 1 to 2 light-years, close enough for gravitational interactions to influence orbital dynamics, but distant enough that stellar collisions remain exceedingly rare. Within these clusters, the distribution of stellar masses follows a predictable pattern known as the initial mass function. For every star with 10 times the Sun's mass, approximately 200 stars form with masses similar to our Sun, and roughly 500 red dwarfs emerge with masses below half the solar value. This ratio means that open clusters contain far more dim, low-massed stars than bright, massive ones, though the luminous giants dominate visual observations. The most massive stars in a cluster, those exceeding 8 solar masses, burn through their hydrogen fuel with furious intensity, their core temperatures reaching 30 million Kelvin or more. These stellar giants will exhaust their nuclear fuel and explode as supernovae within just 10 to 30 million years, while their lower mass siblings continue burning steadily for billions of years. The Hyades, located only 153 light-years away, represents the nearest open cluster to our solar system and provides an exceptional laboratory for studying stellar evolution. At approximately 625 million years old, the Hyades has already lost its most massive original members to supernova explosions, leaving behind a population dominated by stars similar to or smaller than the Sun. The cluster contains roughly 400 confirmed members spread across a volume about 20 light-years in diameter, with the brightest stars forming the distinctive V-shape visible in the constellation Taurus. Aldebaran, the brilliant orange giant that appears to mark one tip of this V, is actually a foreground star located only 65 light-years away, a chance alignment rather than a true cluster member. The gravitational binding of open clusters proves remarkably fragile when measured against cosmic timescales. Unlike the tightly bound globular clusters that orbit the galactic halo, open clusters possess relatively low escape velocities, typically between 1 and 5 kilometers per second. Stars moving faster than this threshold gradually drift away from the cluster, a process accelerated by gravitational encounters with giant molecular clouds and the tidal forces exerted by the galaxy itself. Most open clusters dissolve completely within 200 to 500 million years, their members dispersing into the general stellar population of the galactic disk. The Beehive cluster, also known as Praecep or Messier 44, demonstrates an intermediate stage in this evolutionary process. Located 610 light-years away in the constellation Cancer, this cluster has survived for approximately 600 million years and still retains roughly 1,000 member stars within a diameter of 23 light-years. The cluster's total mass approaches 500 to 600 solar masses, providing sufficient gravitational cohesion to resist complete dissolution for several hundred million years more. Yet even the Beehive shows signs of tidal stripping, with streams of escaped stars extending along its orbital path through the galaxy. Some clusters, however, possess sufficient mass and density to survive for considerably longer periods. The Wild Duck cluster, designated Messier 11, contains approximately 2,900 stars, packed into a region only 14 light-years across, making it one of the most compact and richest open clusters known. Located 6,200 light-years away in the Scutum constellation, this cluster has maintained its integrity for roughly 220 million years, despite its relatively young age. The central density reaches several hundred stars per cubic parsec, creating a stellar environment dramatically different from the sparse surroundings of our own Sun. The distribution of open clusters throughout the Milky Way reveals the ongoing processes of star formation within the galactic disk. Over 1,100 open clusters have been catalogued within our galaxy, though the true number likely exceeds 100,000 when accounting for clusters hidden behind obscuring dust clouds or too distant for current detection methods. These clusters concentrate strongly along the galactic plane, particularly within the spiral arms where molecular clouds accumulate and collapse. The Carina Sagittarius arm and the Perseus arm contain especially rich populations of young clusters, their blue stars tracing the locations of recent and ongoing star formation. The ages of open clusters provide astronomers with a powerful tool for understanding stellar evolution. Because all stars in a cluster formed simultaneously from the same material, they differ primarily in their initial masses. Plotting the brightness and color of cluster members on a diagram reveals a characteristic pattern, the main sequence turn-off point, where stars of a particular mass have exhausted their core hydrogen and begun evolving into giants. The position of this turn-off directly indicates the cluster's age, since more massive stars evolve faster. A cluster showing a turn-off at stars with twice the Sun's mass has an age of roughly 1 billion years, while a turn-off at 10 solar masses indicates an age of only 20 million years. The chemical composition of open clusters also varies systematically with their location in the galaxy. Clusters near the galactic center, where star formation has proceeded most vigorously over cosmic time, tend to contain higher abundances of heavy elements, iron, nickel, and other products of stellar nucleosynthesis. Clusters in the outer galaxy, where fewer generations of stars have lived and died, show lower metallicity. This gradient, measuring roughly 0.05 fewer iron atoms per hydrogen atom for every kiloparsec of distance from the galactic center, records the chemical enrichment history of the Milky Way's disk. Young open clusters often remain partially embedded within their parent molecular clouds, their stars still surrounded by the gas and dust from which they formed. The cluster NGC 2024, located within the Orion B molecular cloud complex, approximately 1,350 light-years away, exemplifies this embedded phase. Infrared observations reveal hundreds of young stars, many still accreting material from circumstellar disks, hidden behind dense curtains of obscuring dust. These protocluster environments represent star formation caught in the act, the gravitational collapse that began perhaps 1 to 2 million years ago, still ongoing as the youngest members continue to accumulate mass. As clusters age and their most massive stars explode as supernovae, the resulting shock waves and radiation pressure gradually disperse any remaining natal gas. This clearing process typically completes within 10 to 30 million years, leaving behind a naked cluster of stars moving together through space. The energy injected by these supernovae may also trigger new rounds of star formation in adjacent molecular clouds, propagating the cycle of stellar birth across the galactic disk in a self-sustaining chain reaction. The study of open clusters extends beyond our own galaxy to the Magellanic Clouds, where thousands of clusters span a remarkable range of ages and masses. The Large Magellanic Cloud alone contains over 4,000 catalogued clusters, including some of the most massive young clusters known anywhere. NGC 1866, located 160,000 light-years away in the Large Magellanic Cloud, contains approximately 100,000 solar masses of stars within a diameter of 100 light-years, approaching the mass of a small globular cluster, while retaining the disk-like distribution and young age characteristic of open clusters. These stellar families, scattered throughout the galactic disk, represent the fundamental units of star formation, the immediate products of molecular cloud collapse before gravitational and tidal forces disperse their members into the general stellar population. Yet some clusters survive far longer than their open counterparts, bound so tightly by gravity that they persist for billions of years as dense spherical concentrations of ancient stars orbiting far from the galactic plane. Those ancient spheres of stars, the globular clusters, stand apart from their younger open cluster cousins in almost every measurable way. Where open clusters contain hundreds or thousands of stars, spread loosely across tens of light-years, globular clusters pack hundreds of thousands to millions of stars into compact spherical volumes, their cores so dense that stellar separations shrink to fractions of a light-year. Where open clusters orbit within the thin disk of the galaxy, following the general rotation of spiral arms and interstellar gas, globular clusters trace elongated elliptical paths that carry them far above and below the galactic plane, plunging through the disk and swinging out into the sparse halo that surrounds the Milky Way like a ghostly envelope. The Milky Way hosts approximately 150 known globular clusters, though the total population may exceed 200 when accounting for those hidden behind the dense dust clouds near the galactic center. These stellar congregations range in mass from roughly 10,000 solar masses, for the smallest examples, to nearly 2.5 million solar masses for Omega Centauri, the most massive globular cluster in our galaxy. Their diameters span from 30 light-years for compact specimens to over 300 light-years for the most extended systems, though the majority of their stars concentrate within central regions measuring just 10 to 30 light-years across. The density within globular cluster cores defies easy comprehension. In the solar neighborhood, stars separate by distances averaging 4 to 5 light-years. Proxima Centauri lies 4.24 light-years from the Sun, and the next nearest system, Barnard's star, sits 5.96 light-years away. Within the core of a dense globular cluster like 47 Tucanae, stellar separations shrink to approximately 0.1 light-years, or roughly 6,300 astronomical units. This represents a stellar density perhaps 10,000 times greater than the Sun's local environment. If Earth orbited a star within such a core, the night sky would blaze with thousands of stars brighter than Venus, and dozens would outshine the full moon. 47 Tucanae itself, visible as a fuzzy patch of light in the southern constellation Tucana, contains approximately 500,000 stars within a diameter of 120 light-years. Its core, measuring just 24 light-years across, holds the highest concentration of these ancient suns. Located 13,000 light-years from Earth, this cluster formed roughly 11.5 billion years ago, when the universe itself was only about 2.2 billion years old. The stars within it have completed more than 50 orbits around the Milky Way's center during their existence, each orbit lasting approximately 220 million years. The age of globular clusters represents their most remarkable characteristic. While open clusters typically disperse within a few hundred million years, globular clusters have persisted since the earliest epochs of galaxy formation. The oldest known globular clusters in the Milky Way date to approximately 12.5 to 13 billion years ago, placing their formation within the first billion years after the Big Bang. This makes them among the oldest structures in the observable universe that remain gravitationally bound and intact. They witnessed the assembly of the Milky Way itself, surviving the chaotic mergers and accretion events that built our galaxy from smaller proto-galactic fragments. This extreme age manifests in the chemical composition of globular cluster stars. Elements heavier than hydrogen and helium, what astronomers call metals, form primarily within stellar cores and supernova explosions, accumulating in the interstellar medium over successive generations of star formation. The earliest stars formed from nearly pure hydrogen and helium, the primordial elements created in the Big Bang. Globular cluster stars, born before the galaxy had enriched itself through billions of years of stellar nucleosynthesis, contain metal abundances ranging from just 0.1% to 10% of the Sun's metallicity. The cluster M92, located 26,700 light-years away in the constellation Hercules, contains stars with iron abundances roughly 0.5% that of the Sun, marking it as one of the most metal-poor globular clusters known. The color of globular clusters reflects this ancient population. Young stars burn blue and hot, their massive members consuming hydrogen fuel at prodigious rates before exploding as supernovae within tens of millions of years. In a 12-billion-year-old cluster, all stars more massive than approximately 0.8 solar masses have long since exhausted their fuel and evolved off the main sequence. The remaining population consists predominantly of red dwarfs, orange dwarfs, and the evolved remnants of formerly massive stars: red giants, horizontal branch stars, and white dwarfs. This gives globular clusters their characteristic golden or reddish hue, a visual signature of their antiquity visible even in small telescopes. The Hertzsprung-Russell diagrams of globular clusters serve as cosmic chronometers. By identifying the point at which stars begin leaving the main sequence, the so-called turn-off point, astronomers can determine cluster ages with precision approaching a few 100 million years. In young clusters, the turn-off occurs at high luminosities and blue colors, indicating that massive, short-lived stars still populate the main sequence. In ancient globular clusters, the turn-off has migrated down to stars of roughly 0.8 solar masses, with surface temperatures around 5,800 Kelvin, similar to our Sun but slightly cooler and less luminous. Stars above this mass have already evolved into red giants or collapsed into white dwarfs. The formation of globular clusters remains partially mysterious, though observations have revealed crucial details. These systems almost certainly formed during intense episodes of star formation in the early universe, when dense gas clouds collapsed rapidly under gravity. The conditions required to produce such massive, compact stellar systems appear to have been more common in the young universe, when gas densities were higher and galaxy mergers more frequent. Some globular clusters may have formed within dwarf galaxies that were later absorbed by the Milky Way, their stellar population surviving as intact clusters even as their parent galaxies were tidally disrupted. Evidence for this accretion history comes from the orbits and chemical compositions of different globular cluster populations. The Milky Way's globular clusters divide roughly into two groups: a metal-poor halo population with highly elliptical, randomly oriented orbits, and a more metal-rich disk population with orbits closer to the galactic plane. The halo clusters likely formed in the chaotic early assembly of the galaxy, or within accreted satellite galaxies, while the disk clusters may have formed later within the more organized structure of the developing Milky Way. The gravitational dynamics within globular clusters produce phenomena rarely seen elsewhere. The high stellar densities enable frequent close encounters between stars, leading to gravitational interactions that can exchange energy and angular momentum between cluster members. Over billions of years, these encounters cause massive stars to sink toward the cluster center, while lighter stars migrate outward, a process called mass segregation. The cores of old globular clusters thus become dominated by stellar remnants, white dwarfs, neutron stars, and in some cases, stellar mass black holes that have accumulated near the gravitational center. These dense cores also facilitate the formation of exotic stellar systems. Blue stragglers, Stars that appear younger and bluer than they should given the cluster's age form through stellar collisions or mass transfer in binary systems, processes enhanced by the crowded conditions. X-ray binaries, in which a neutron star or black hole accretes matter from a companion star, occur at rates hundreds of times higher in globular clusters than in the general galactic field. Millisecond pulsars, neutron stars spun up to rotation periods of just a few milliseconds through accretion, concentrate in globular clusters. The cluster Terzan 5 alone contains at least 37 known millisecond pulses. Some globular clusters may harbor intermediate mass black holes at their centers, objects with masses between 100 and 100,000 solar masses, bridging the gap between stellar mass black holes and the supermassive black holes found in galactic nuclei. Omega Centauri, with its unusually large mass and complex stellar populations, shows kinematic evidence suggesting a central black hole of approximately 40,000 solar masses. If confirmed, such objects would represent the seeds from which supermassive black holes may have grown in the early universe, preserved within the ancient stellar systems that witnessed the dawn of galaxy formation. The tidal forces exerted by the Milky Way gradually strip stars from the outer regions of globular clusters, creating long stellar streams that trace the cluster's orbital paths across the sky. The Palomar 5 cluster, located 75,000 light-years away, has lost so many stars to tidal stripping that its stellar streams extend over 30,000 light-years, containing more mass than the cluster itself retains. In another few billion years, Palomar 5 will dissolve entirely, its remaining stars dispersing into the galactic halo as individual field stars indistinguishable from the general stellar population. Yet the most massive and compact globular clusters will survive far longer, their gravitational binding energy sufficient to resist tidal disruption for timescales exceeding the current age of the universe. These ancient spheres of stars, orbiting through the sparse halo surrounding the Milky Way's luminous disk, represent fossils from the epoch of galaxy formation, self-contained stellar systems that have maintained their integrity across cosmic time, while the galaxy itself assembled around them. Their stars, their orbits, and their chemical compositions encode information about conditions in the universe when it was less than a tenth of its current age. Between these dense stellar concentrations, and between the stars within them, stretches a medium far more tenuous than any laboratory vacuum. Yet this diffuse material, the gas and dust pervading interstellar space, contains the raw ingredients from which all stars and clusters ultimately form. That diffuse material, the interstellar medium, fills the vast gulfs between stars with a substance so rarefied that it would register as a near-perfect vacuum by any terrestrial standard. Yet this tenuous ocean of gas and dust constitutes roughly 15% of the Milky Way's visible mass, spread across a volume so immense that even at densities of just 1 atom per cubic centimeter, the total material amounts to billions of solar masses waiting to participate in the next generation of stellar birth. The interstellar medium exists in several distinct phases, each characterized by different temperatures, densities, and physical states that coexist throughout the galaxy, like layers of atmosphere on a planetary scale. The hottest phase, the coronal gas, reaches temperatures exceeding 1 million Kelvin, heated by the shock waves from supernova explosions that have swept through the galactic disk over billions of years. This superheated plasma fills enormous bubbles and tunnels carved through denser material, glowing faintly in X-rays and occupying perhaps half the volume of the galactic disk, despite containing only a tiny fraction of its mass. Within these hot bubbles, atoms have been stripped of their electrons entirely, creating a plasma so diffuse that particles may travel for light years before encountering another atom. Surrounding and interpenetrating this hot phase lies the warm ionized medium, gas heated to temperatures around 8,000 Kelvin by ultraviolet radiation streaming from hot, young stars. This phase glows with the characteristic red light of hydrogen alpha emission, the same light that illuminates the Great Emission Nebulae, though spread far more thinly across the spaces between those concentrated star-forming regions. Radio astronomers detect this ionized gas through its effect on pulsar signals, which arrive slightly delayed at lower frequencies as they pass through the free electrons scattered along the line of sight. By measuring this dispersion, astronomers can map the distribution of ionized material throughout the galaxy, revealing a layer concentrated toward the galactic plane, but extending thousands of light years above and below the disk. The warm neutral medium occupies a similar temperature range, but consists of hydrogen atoms that have retained their single electrons, neither ionized nor bound into molecules. At temperatures near 6,000 Kelvin, these atoms emit and absorb radiation at a wavelength of 21 centimeters, corresponding to a subtle transition in the spin alignment between the proton and electron that constitutes each hydrogen atom. This 21-centimeter line has become one of the most powerful tools for mapping the structure of our galaxy and others, revealing spiral arms, streaming motions, and the overall rotation curve that first hinted at the presence of dark matter. The warm neutral medium fills perhaps 40% of the galactic volume, serving as a reservoir from which denser clouds can condense when conditions favor gravitational collapse. Cooler still, the cold neutral medium exists at temperatures between 50 and 100 Kelvin, dense enough that atoms begin to shield one another from the ambient radiation that would otherwise keep them warm. These cold clouds contain roughly 100 atoms per cubic centimeter, still extraordinarily tenuous by terrestrial standards, but dense enough to block background starlight and create the dark patches visible against the luminous band of the Milky Way. Within these cold clouds, hydrogen atoms occasionally collide and stick together, forming molecular hydrogen that marks the transition to an even denser phase of the interstellar medium. The molecular clouds represent the coldest and densest component of the interstellar medium, with temperatures dropping to just 10 or 20 Kelvin and densities climbing to thousands or even millions of particles per cubic centimeter. At these frigid temperatures, hydrogen exists almost entirely in molecular form, paired atoms that emit no convenient radio signature comparable to the 21-centimeter line of atomic hydrogen. Instead, astronomers trace molecular clouds through carbon monoxide, a molecule roughly 10,000 times less abundant than hydrogen, but far easier to detect through its rotational emission lines at millimeter wavelengths. The ratio of carbon monoxide to hydrogen remains approximately constant throughout most molecular clouds, allowing observers to estimate the total mass of molecular material from the intensity of carbon monoxide emission. These molecular clouds range in size from small clumps a few light-years across to giant molecular cloud complexes spanning hundreds of light-years and containing millions of solar masses of material. The Orion molecular cloud, located roughly 1,300 light-years from Earth, stretches across much of the constellation and contains enough material to form hundreds of thousands of stars. Within such clouds, the densest cores have already begun collapsing, their internal gravity finally overwhelming the thermal pressure, magnetic support, and turbulent motions that had previously held them in equilibrium. Dust comprises only about 1% of the interstellar medium by mass, yet this small fraction profoundly shapes the appearance and behavior of the galaxy. These microscopic grains, ranging from a few nanometers to about a micrometer in size, consist primarily of silicates and carbonaceous materials forged in the outer atmospheres of dying stars and expelled into space by stellar winds and supernova explosions. Each grain represents a tiny fragment of stellar ash, carrying atoms that were synthesized through nuclear fusion in stellar cores and then processed through the complex chemistry of circumstellar envelopes. Interstellar dust absorbs and scatters starlight, preferentially affecting shorter wavelengths and causing distant stars to appear redder than their intrinsic colors would suggest. This interstellar reddening increases with distance, making stars behind dense dust clouds appear not only dimmer, but also shifted toward the red end of the spectrum. Astronomers must carefully correct for this effect when determining the true properties of distant stars, using the observed reddening to estimate the amount of intervening dust along each line of sight. In the densest molecular clouds, dust extinction can exceed 30 magnitudes at visible wavelengths, meaning that less than 1 photon in a trillion makes it through to the other side. Yet dust also plays a constructive role in the chemistry of the interstellar medium. The surfaces of dust grains provide sites where atoms can meet and react, forming molecules that would rarely assemble through random collisions in the gas phase. Molecular hydrogen itself forms primarily on dust-grained surfaces, where hydrogen atoms can stick, migrate, find partners, and combine before being released back into the gas. More complex molecules, including water, ammonia, methanol, and even amino acids, have been detected in molecular clouds, their formation facilitated by the catalytic surfaces of interstellar dust. The interstellar medium does not remain static, but flows continuously through the galaxy, driven by stellar winds, supernova explosions, and the differential rotation of the galactic disk. Hot gas from supernova remnants expands outward, sweeping up cooler material into dense shells that may eventually fragment and collapse to form new stars. Spiral density waves compress the interstellar medium as it passes through the galaxy's arms, triggering the formation of giant molecular clouds that will spawn the next generation of massive stars. These stars will live fast, die young, and return enriched material to the interstellar medium, gradually increasing its content of heavy elements over cosmic time. The chemical evolution of the interstellar medium records the cumulative history of stellar nucleosynthesis in the galaxy. When the Milky Way was young, its gas consisted almost entirely of hydrogen and helium, the primordial elements forged in the first minutes after the Big Bang. Each generation of stars has added heavier elements to this mix, from the carbon and oxygen produced in the cores of intermediate mass stars to the iron synthesized in the final moments before core collapse supernovae. Today, roughly 2% of the atoms in the interstellar medium are elements heavier than helium, a small fraction that nonetheless includes all the raw materials necessary for rocky planets and organic chemistry. This enriched material does not distribute itself uniformly throughout the galaxy. The inner regions, where star formation has proceeded most vigorously over cosmic time, contain higher concentrations of heavy elements than the outer disk, where fewer generations of stars have lived and died. Globular clusters, formed from primordial gas before significant enrichment had occurred, contain stars with heavy element abundances 100 times lower than the Sun, while young stars forming today in the solar neighborhood inherit a full complement of the elements their predecessors created. The interstellar medium extends far beyond the thin disk where most stars reside, forming a halo of diffuse gas that surrounds the Milky Way and extends for hundreds of thousands of light years. This circumgalactic medium contains material expelled from the disk by supernova-driven winds, gas falling inward from intergalactic space, and remnants of smaller galaxies that have been tidally disrupted during close encounters. The mass of this extended halo may rival or exceed the mass of gas within the disk itself, representing a reservoir that can replenish the raw materials for star formation as the disk gradually consumes its current supply. Beyond the halo of individual galaxies, the intergalactic medium fills the spaces between galaxies with gas even more tenuous than the interstellar medium, yet containing the majority of ordinary matter in the universe. This cosmic web of diffuse gas, heated by gravitational collapse and ultraviolet radiation from distant quasars, connects galaxies through filaments of warm material that trace the underlying structure of dark matter. Those vast islands of stars, the galaxies, represent the fundamental units of cosmic organization above the scale of individual stellar systems. Each galaxy contains not merely thousands or millions of stars, but hundreds of billions of them, bound together by gravity into structures spanning tens of thousands to hundreds of thousands of light years across. The Milky Way itself, our home galaxy, contains somewhere between 200 billion and 400 billion stars, a number so large that if one could count them at a rate of 1 per second, the task would require more than 6,000 years to complete. The word galaxy derives from the Greek galaxias, meaning milky, a reference to the pale band of light that stretches across Earth's night sky. For millennia, observers could only wonder at this luminous river overhead, unable to resolve its true nature. Not until Galileo Galilei turned his telescope towards the Milky Way in 1610 did humanity glimpse the truth. That soft glow consisted of countless individual stars, too numerous and too distant to distinguish with the naked eye. Yet even this revelation left the deeper question unanswered. Were these stars the entirety of the universe, or merely one island among many? The answer came slowly, through centuries of increasingly precise observation. In 1755, the philosopher Immanuel Kant proposed that certain fuzzy patches of light visible through telescopes might be vast collections of stars, so distant that they appeared as mere smudges. This hypothesis remained controversial for over a century and a half. The critical evidence arrived in 1923, when Edwin Hubble identified Cepheid variable stars in the Andromeda Nebula, as it was then called. These pulsating stars, whose intrinsic brightness correlates precisely with their pulsation period, served as cosmic distance markers. Hubble's measurements revealed that Andromeda lay approximately 900,000 light-years away, a distance later revised upward to 2.537 million light-years. This placed it far beyond the boundaries of the Milky Way, confirming that our galaxy was merely one among billions. The structure of a typical spiral galaxy like the Milky Way reveals the interplay of gravity, rotation, and time across cosmic scales. At the center lies a dense bulge of older, redder stars, a roughly spherical concentration that may extend several thousand light-years in radius. The Milky Way's bulge contains stars that formed within the first few billion years of the galaxy's existence, their orbits carrying them on elongated paths that take them high above and below the galactic plane. Surrounding this bulge, a bar-shaped structure of stars stretches approximately 27,000 light-years from end to end, channeling gas inward toward the central regions and triggering bursts of star formation along its length. Extending outward from this central bar, the spiral arms wind through the galactic disk like the arms of a pinwheel, though their true nature differs from their appearance. These arms are not solid structures through which stars travel, but rather density waves, regions of compressed gas, and enhanced star formation that propagate through the disk like ripples across water. Stars enter these regions, linger briefly as the compression triggers the birth of new stellar generations, then exit on the other side, continuing their orbits around the galactic center. The brightest, most massive stars born in these regions burn through their fuel so quickly that they die before leaving the arm, creating the illusion that the arms themselves are permanent features rather than transient patterns of enhanced activity. The disk of the Milky Way extends approximately 100,000 light-years in diameter, though recent observations suggest the outermost regions may stretch even farther, to perhaps 200,000 light-years when including the warped and flared outer edges. This disk maintains a remarkable thinness relative to its width, averaging only about 1,000 light-years in thickness through most of its extent. If the galaxy were scaled down to the size of a compact disk, the disk would be thinner than a sheet of paper. Within this flattened structure, the Sun orbits at a distance of approximately 26,000 light-years from the galactic center, completing one circuit every 230 million years at a velocity of roughly 220 kilometers per second. The mass required to hold these billions of stars in their orbits vastly exceeds what the visible matter alone could provide. Observations of stellar velocities in the outer regions of galaxies, beginning with Vera Rubin's work in the 1970s, revealed that stars at the galaxy's edge orbit at speeds that should fling them into intergalactic space if only visible matter were present. The solution to this puzzle lies in dark matter, an invisible substance that neither emits nor absorbs light, but exerts gravitational influence on everything around it. The Milky Way's dark matter halo extends far beyond the visible disk, perhaps to a radius of 300,000 light-years or more, containing roughly 1 trillion solar masses of this mysterious material, roughly 10 times the mass of all the stars, gas, and dust combined. At the very heart of the Milky Way, hidden behind dense clouds of gas and dust that block visible light, lies Sagittarius, a star, a supermassive black hole containing approximately 4 million times the mass of the Sun compressed into a region smaller than Mercury's orbit. This gravitational monster reveals itself through the motions of stars in its immediate vicinity, some of which complete orbits in as little as 16 years, while traveling at speeds exceeding 3% of the speed of light. Despite its enormous mass, Sagittarius A star currently accretes matter at a relatively modest rate, producing only faint radio and X-ray emissions compared to the brilliant quasars that mark actively feeding black holes in distant galaxies. The Milky Way does not drift through space in isolation. Gravitational bonds connect it to dozens of smaller companion galaxies, the most prominent being the Large and Small Magellanic Clouds, visible from Earth's southern hemisphere as detached fragments of the Milky Way's glow. The Large Magellanic Cloud, located approximately 160,000 light-years away, contains roughly 30 billion stars and spans 14,000 light-years in diameter. Its smaller companion lies slightly farther, at 200,000 light-years, containing perhaps 3 billion stars. Both galaxies are slowly spiraling inward, their orbits decaying through dynamical friction as they plow through the Milky Way's dark matter halo. In approximately 2 billion years, the Large Magellanic Cloud will make its closest approach, potentially triggering a burst of star formation in both galaxies. Beyond these nearby companions, the Andromeda Galaxy approaches at approximately 110 kilometers per second, closing the 2.5 million light-year gap that currently separates us. In roughly 4.5 billion years, the two galaxies will begin their first close passage, their mutual gravity distorting both into elongated streamers of stars and gas. Over the following billion years, they will separate, slow, and fall back together repeatedly, eventually merging into a single elliptical galaxy that astronomers have nicknamed Milky Way. The stars themselves will rarely collide during this merger, as the distances between them remain vast, even as the galaxies interpenetrate. But the gas clouds will compress and shock against each other, triggering intense bursts of star formation that will briefly illuminate the merged system with the blue light of young, massive stars. The diversity of galaxy forms extends far beyond spirals like the Milky Way. Elliptical galaxies, ranging from nearly spherical to highly elongated, contain predominantly older, redder stars, and little of the gas and dust that fuels ongoing star formation. The largest of these, the giant ellipticals found at the centers of galaxy clusters, may contain 10 trillion stars and span several 100,000 light-years in diameter. At the opposite extreme, dwarf galaxies containing only a few million stars orbit as satellites around larger hosts, their shallow gravitational wells making them vulnerable to tidal disruption during close encounters. These countless islands of stars, scattered across the observable universe in numbers exceeding 2 trillion, do not distribute themselves randomly through space. Gravity draws them together into groups, clusters, and superclusters, creating a hierarchy of structure that extends to the largest scales the universe permits. Among those 2 trillion galaxies scattered across the observable universe, roughly 2/3 display the distinctive pattern that astronomers call spiral structure. These spiral galaxies, including our own Milky Way, represent some of the most visually striking objects in the cosmos, their sweeping arms of stars, gas, and dust curving outward from luminous central regions in patterns that have fascinated observers since Lord Rosse first resolved the spiral structure of M51 through his massive telescope in 1845. The spiral arms themselves present one of the most elegant puzzles in astrophysics. At first glance, they appear to be physical structures, rivers of stars flowing outward from galactic centers. Yet this interpretation creates an immediate problem. Stars in spiral galaxies do not orbit at uniform speeds. Those closer to the center complete their orbits far more quickly than those in the outer regions. The Sun, located roughly 26,000 light-years from the Milky Way's center, takes approximately 230 million years to complete one galactic orbit, traveling at about 220 kilometers per second. Stars at half this distance orbit in perhaps 100 million years, while those at twice this distance require over 400 million years. If spiral arms were simply collections of stars moving together, this differential rotation would wind them up completely within a few galactic rotations, destroying the spiral pattern entirely. Yet spiral galaxies have existed for billions of years, their arms remaining distinct across cosmic time. The resolution to this winding problem came through the density wave theory, developed in the 1960s by Chia Qiao-Lin and Frank Xu. The spiral arms are not material structures, but rather waves of compression that propagate through the galactic disk, much like the compression waves that create sound or the traffic jams that form on highways, even when no obstacle blocks the road. Stars and gas clouds pass through these density waves, slowing as they enter regions of enhanced gravitational attraction, then accelerating as they exit. The wave pattern rotates as a rigid structure, maintaining its shape while individual stars drift through it on their own orbital paths. A star like the Sun has passed through multiple spiral arms during its 4.5 billion year existence, spending perhaps 10 million years within each arm before emerging into the lower density regions between them. This density wave model explains the characteristic appearance of spiral arms. As interstellar gas enters a spiral arm, the compression triggers gravitational collapse in molecular clouds that might otherwise have remained stable. New stars form preferentially within the arms, and the most massive among them, the blue giants with surface temperatures exceeding 20,000 Kelvin, burn through their hydrogen fuel so rapidly that they exhaust their nuclear reserves within a few million years. These brilliant stars illuminate the spiral arms with their intense blue-white light, then explode as supernovae before they can drift far from their birthplaces. The arms thus appear blue and luminous, not because they contain more stars overall, but because they contain a disproportionate number of young, hot, short-lived stars that have not yet had time to migrate away. The Milky Way itself displays this spiral structure, though our position within the galactic disk makes the pattern difficult to observe directly. Radio astronomers mapping the distribution of hydrogen gas and infrared telescopes peering through the obscuring dust have revealed that our galaxy possesses two major spiral arms, the Scutum Centaurus arm and the Perseus arm, along with several smaller armlets and spurs. The Sun resides within one of these minor structures, the Orion Spur, a bridge of stars and gas connecting the larger arms. From our vantage point, the Milky Way's spiral structure manifests as the band of concentrated starlight that arcs across the night sky, the combined glow of billions of stars too distant to resolve individually, their light blending into a luminous river that ancient observers interpreted as spilled milk or a celestial pathway. Spiral galaxies divide into several subcategories based on the tightness of their arms and the prominence of their central bulges. The Hubble classification scheme, developed in the 1920s and refined over subsequent decades, arranges spirals along a sequence from SA through SD. So galaxies possess tightly wound arms and large central bulges dominated by older, redder stars. SD galaxies display loosely wound arms and minimal bulges, their disks extending nearly to their centers. The Milky Way falls somewhere in the middle of this sequence, classified as an SBBC galaxy, the B indicating the presence of a central bar. These barred spirals, which constitute roughly 2/3 of all spiral galaxies, possess an elongated structure of stars extending across their central regions, with the spiral arms emerging from the ends of the bar rather than from the nucleus itself. The bar itself forms through gravitational instabilities in the galactic disk, as stars on slightly elliptical orbits align their orbital orientations, creating a coherent, elongated structure that can span tens of thousands of light years. The Milky Way's bar extends approximately 27,000 light years from end to end, oriented at roughly 45 degrees to our line of sight toward the galactic center. This bar channels gas inward toward the central regions, potentially feeding the supermassive black hole that lurks at the galaxy's heart, and triggering episodes of enhanced star formation in the nuclear regions. The rotation curves of spiral galaxies provided some of the earliest and most compelling evidence for the existence of dark matter. Astronomers expected that stars and gas in the outer regions of galaxies would orbit more slowly than those closer to the center, following the same pattern that governs planetary orbits in our solar system, where Mercury races around the Sun at 47 kilometers per second, while distant Neptune crawls along at barely 5. Yet observations revealed that spiral galaxy rotation curves remain essentially flat at large radii, with stars at the visible edges of galaxies orbiting just as quickly as those much closer to the center. This unexpected behavior implies the presence of enormous quantities of unseen mass extending far beyond the visible disk, a dark matter halo that may contain 5 to 10 times as much mass as all the luminous matter combined. The Andromeda Galaxy, designated M31, provides the nearest example of a large spiral galaxy beyond our own, lying approximately 2.5 million light-years distant in the direction of the constellation that bears its name. spanning roughly 220,000 light-years in diameter. Andromeda appears larger than the Milky Way, though recent measurements suggest the two galaxies possess comparable total masses when their dark matter halos are included. Andromeda's spiral structure, visible even through modest telescopes as dust lanes silhouetted against the galaxy's luminous bulge, includes a prominent ring of star formation at a radius of roughly 32,000 light-years from the center, possibly triggered by a collision with a smaller companion galaxy several 100 million years ago. The two galaxies approach each other at approximately 110 kilometers per second, drawn together by their mutual gravitational attraction. In roughly 4.5 billion years, Andromeda and the Milky Way will begin their first close passage, their spiral structures distorting under tidal forces as stars are flung outward into long tidal tails. Over the following billion years, the two galaxies will merge completely, their spiral arms dissolving as the ordered rotation of their disks transforms into the random stellar motions characteristic of elliptical galaxies. The resulting merged system, sometimes called Milkomeda or Milkdromeda, will contain the combined stellar populations of both parent galaxies, though the vast distances between individual stars mean that actual stellar collisions will be extraordinarily rare. This fate illustrates a broader truth about spiral galaxies. They represent a particular phase in galactic evolution rather than a permanent state. Spiral structure requires a rotating disk of gas and stars, maintained by ongoing accretion of fresh material and protected from the disruptive effects of major mergers. Galaxies that exhaust their gas supplies or experience violent collisions lose their spiral patterns, their stars settling into the more random configurations of elliptical or lenticular systems. The prevalence of spiral galaxies in the present-day universe reflects the relatively quiescent cosmic environment that has prevailed since the peak of galaxy merger activity several billion years ago. Yet spiral galaxies do not exist in isolation. Gravity draws them toward their neighbors, gathering them into associations that range from small groups containing a handful of members to massive clusters harboring thousands of galaxies bound together within shared dark matter halos.